Good morning to everybody. Καλημέρα σας. I will address the beginning of the conference in Greek because this is the 10th anniversary of the conference, so I would like to use our language. Όπως είπα, είναι η 10η επέτειος αυτού του συνεδρίου που ξεκίνησε το 2014 και είναι ορόσημο κατά κάποιο τρόπο για αυτό το συνέδριο, το οποίο συμβαίνει πάντα στο Πανεπιστήμιο Αθηνών, στους χώρους του Πανεπιστήμιου Αθηνών. Θέλω να ευχαριστήσω το Πανεπιστήμιο για την αρρωγή όλα αυτά τα χρόνια και ελπίζουμε να συνεχίσει και στο μέλλον. Γι' αυτό το ορόσημο έχουμε τη χαρά και την τιμή να έχουμε μαζί μας τον πρίτανη του Πανεπιστημίου Αθηνών, τον καθηγητή του Τμήματος Ιατρικής Γεράσιμο Σιάσο, ο οποίος θα ξεκινήσει και το συνέδριο.
Αγαπητές και αγαπητοί συνάδελφοι, αγαπητές φοιτήτριες, αγαπητοί φοιτητές, είναι ιδιαίτερη χαρά μου να βρίσκομαι σήμερα μαζί σας και να σας καλωσορίσω στο ετήσιο συνέδριο θεωρητικής φυσικής, το οποίο διοργανώνει το Τμήμα Φυσικής του Εθνικού και Καποδιστριακού Πανεπιστημίου Αθηνών. Το συνέδριο αυτό, αναφέρθηκε και ο εκλεκτός φίλος κ. Φέτσος, αποτελεί ένα σταθερό θεσμό, ο οποίος έχει ως στόχο να φέρει κοντά τόσο καταξιωμένους νέους στην Ελλάδα αλλά και εκτός της Ελλάδας και να αναδείξει τα πρόσφατα ερευνητικά αποτελέσματα στον ευρύτερο χώρο της θεωρητικής φυσικής, ενισχύοντας με αυτόν τον τρόπο τον επιστημονικό διάλογο. Η φετινή διοργάνωση, όπως αναφέρθηκε, έχει μία ξεχωριστία σηματοδοτούμενη συμπλήρωση δεκαετών επιστημονικών του συγκεκριμένου. Στη διάρκεια αυτής της δεκαετίας το συνέδριο εξελίχθηκε σε σημείο αναφοράς, συμβάλλοντας στη διάχυση της γνώσης, στην διάχυση των ερευνητικών αποτελεσμάτων και στην διαμόρφωση σταθερών συνεργασιών του Πανεπιστημίου μας με άλλα ιδρύματα εκτός Ελλάδας. Έχει ιδιαίτερη αυτή και η συμμετοχή ερευνητών, οι οποίοι βέβαια αρκετοί από αυτούς επιστημονικές σχέσεις με το Ίδρυμά μας όλα αυτά τα χρόνια. Σε πολλές περιπτώσεις κλινική οπότε αυτό προσθέτει ακόμα περισσότερο στην στρατηγική του Πανεπιστημίου, μια στρατηγική εξωστρέφειας, μια στρατηγική διεθνοποίησης, μια στρατηγική να φέρει κοντά και Έλληνες με το πανεπιστήμιό μας, αλλά και διακεκριμένους επιστήμονες από πολλά πανεπιστήμια ανεξαρτήτου καταγωγής. Θα ήθελα λοιπόν να εκφράσω τις εγκάρδιες ευχαριστίες και συγχαρητήρια σε όλα τα μέλη της Επιτροπής που έχουν συνεισφέρει όλη αυτή τη δεκαετία για αυτό το συνέδριο. Θα τους αναφέρω έτσι αλφαβητικά: τους καθηγητές Άρη Μουστάκα, Ιωάννη Παπαδημητρίου, Γεώργιο Παπαθανασίου, Κωνσταντίνος Φέτσο και Βασίλειο Σπανό από το Πανεπιστήμιό μας. Αναφέρω τους από το βέβαια είναι και άλλοι διακεκριμένοι συνάδελφοι από άλλα πανεπιστήμια. Η συμβολή τους υπήρξε καθοριστική για να φτάσει αυτό το συνέδριο να έχει αυτό το αποτύπωμα την δεκαετία αυτή. Οι εκδηλώσεις όπως αυτές ενισχύουν το αποτύπωμα του Πανεπιστημίου μας στο διεθνές ακαδημαϊκό στερέωμα και επιβεβαιώνουν τη στρατηγική μας για δημιουργική συνεργασία μεταξύ των ελληνικών ιδρυμάτων αλλά και διεθνών ερευνητικών φορέων. Να πω και στο τμήμα φυσικής, το οποίο είναι το μεγαλύτερο τμήμα της Σχολής Θετικών Επιστημών και θα ήθελα να μεταφερθεί και προς το τμήμα, είναι πολλά διακεκριμένα μέλη του εδώ, η στήριξη την οποία έχει αποφασίσει η διοίκηση τα τελευταία 2 χρόνια να παρέχει σε ένα τμήμα το οποίο αποτελεί έναν από τους βασικότερους παράγοντες ανόδου του Πανεπιστημίου μας και στις διεθνείς λίστες αξιολόγησης, καθώς πολλά διακεκριμένα μέλη από το τμήμα φυσικής συγκαταλέγονται στους κορυφαίους Έλληνες ερευνητές. Αυτό δεν έχουμε μείνει τα τελευταία 2 χρόνια μόνο στα λόγια. Έχουμε προσπαθήσει να στηρίξουμε πάρα πολύ το τμήμα φυσικής. Να σας πω ότι τα τελευταία 2 χρόνια έχουμε κατανείμει 9 νέες θέσεις καθηγητών στο τμήμα φυσικής. Είναι οι περισσότερες θέσεις που κατανεμηθεί ποτέ στο τμήμα φυσικής σε τόσο σύντομο διάστημα. Έχουμε αυξήσει τη χρηματοδότηση του τμήματος για τις λειτουργικές του ανάγκες κατά 20% και έχουμε κατανείμει επιπλέον περίπου $500,000 για όργανα από το πρόγραμμα Αριστεία, με σκοπό να καλύψουμε αυτό το έλλειμμα που υπήρχε και σε πολλά άλλα τμήματα όσον αφορά την ανανέωση του ερευνητικού εξοπλισμού. Κλείνοντας λοιπόν, να ευχαριστήσω την Οργανωτική Επιτροπή, να ευχαριστήσω όλο το προσωπικό του Τμήματος Φυσικής για το εξαιρετικό έργο που επιτελούν και να ευχηθώ καλή επιτυχία στις εργασίες του συνεδρίου. Θα με συγχωρέσετε, δεν θα παραμείνω στην αίθουσα, γιατί οι υποχρεώσεις είναι και άλλες και πρέπει να βρίσκομαι σε άλλα 2 μέρη μέσα στην επόμενη μισή ώρα. Καλή επιτυχία λοιπόν στις εργασίες του συνεδρίου.
Ευχαριστούμε πολύ. Okay, we are ready to start with the scientific part of the conference. So our first speaker is Tassos Pekkou, who is a professor at the University of Thessaloniki, and he's going to talk about the thermal representation of conformal ladder integrals. Tassos, we'll do 10 minutes before.
Καλημέρα σας. Thank you very much. Let me also say 2 words in Greek. Θέλω να ευχαριστήσω το τμήμα για την πρόσκληση. Θέλω να πω και εγώ, όπως είπε και ο κύριος Πρίτανης, ότι είναι πολύ σημαντική αυτή η εκδήλωση του συνεδρίου που γίνεται εδώ πέρα. Κυρίως θα έλεγα προσωπικά να απευθύνω τα συγχαρητήρια στον συνάδελφο τον Κώστα και φίλο. Το συνέδριο έχει καθιερωθεί. Είναι πλέον κάτι το οποίο πρέπει το τμήμα σας, το Πανεπιστήμιο, να το προφυλάξει και να το διευρύνει. Και όπως πρέπει επίσης, αν ήταν εδώ ο κύριος Πίτανης, θα του έλεγα ότι εδώ το συνέδριο ασχολείται με ίσως την πιο θεμελιώδη μορφή βασικής έρευνας που υπάρχει και αυτό το πόσο σημαντική είναι η βασική έρευνα στην επιστήμη το γνωρίζουμε πολύ καλά εμείς οι ακαδημαϊκοί, όχι μόνο στην Ελλάδα και στο εξωτερικό. Είναι το διαμάντι της έρευνας, το οποίο φωτίζει και ζεσταίνει τα πάντα και έχουμε την υποχρέωση αυτό το πράγμα να το μεταδώσουμε στην ελληνική κοινωνία, διότι τελευταία αυτό δεν έχει γίνει τόσο πολύ κατανοητό, πόσο σημαντικό είναι αυτό το κομμάτι της βασικής έρευνας για όλο τον ακαδημαϊκό χώρο. So, now I switch to the real stuff. I will talk about some work that we did in the past couple of years with Manthos Karidas. With Manthos Karidas, Songyan Lee and Mathieu Vilat, that connects thermal physics to conformal physics in a way that we still don't understand, but we hope that it will produce something interesting. I think we believe that it hides something beneath the surface that we need to understand. So the big picture that it looks that it emerges vaguely is a connection between quantum mechanics, thermal quantum field theory, the mathematical theory of single value polylogs, which is connected with conformal ladder integrals, and maybe holography in the context of ADS2 CFT1. This is very schematic at the moment, and I hope that I will shed the light into some of these issues in my talk. So, what are conformal ladder integrals that I will be talking about? Conformal ladder integrals appear in the calculation of 4-point functions, and 4-point functions are fundamental objects in conformal field theory because they encode the dynamics of the CFT through the operator product expansion. As we all know, they can be bootstrapped using symmetry and unitarity, and there has been a long activity in this direction over the past, say, 10-15 years. But nevertheless, they can also be calculated, as we learn in school, by perturbative calculations, which means by integrals. And they are very nice and very beautiful because conformal symmetry simplifies the corresponding integrals. And in particular, the ladder integrals that I will be talking about, they are a special class of these conformal integrals, which have a very nice structure. They have appeared in ADS-CFT recurrently, more recently in the context of Mellin transforms, and they have applications in fishnet type theories, large N calculations, integrability, and the mathematics theory of single valued polylogs. Now, the ladder integrals appear in n equal 4 Springer Mills in the planar limit, in the fishnet theories that I will be talking about later, in large charged expansions, in integrability studies, in the so-called Basso-Dixon integrals, and recently in thermal bootstrap calculations. So, what are these conformal ladder integrals? So, schematically, they look like the thing above. The integrals, they have an explicit form that is shown here below. The ladder integrals are 4-point functions with legs, massless legs, as shown here, two different kinds of massless propagators, which in some conformal limit, as I will again explain, they become 3-point functions. One point is at zeta, the other is at 1, and the other point is at 0, and these legs correspond to the number of loops. So now why they are called loops, etc., because there is a transformation of these integrals, a kinematical transformation, to the usual momentum loop integrals that we do in quantum field theory. There have been a lot of work on this direction in the recent past, but I'm not going to review that. So the fact is that there are some integrals that are multi-loop and they have this very interesting form. Okay. Why these integrals are manageable? Because they have some interesting properties like conformal covariance, that is, apart from the Lorentz and Poincaré invariance, if I scale all the x's, they behave in this way. I notice that I use K and L. These are two parameters that they will follow me through the talk. If you didn't notice, I think this is a little bit interesting. K is related to the number of dimensions of the integral by d equals 2k plus 2. So I'm always in even dimension integral, interdimensional integrals. And L is the number of loops. Okay, I just wanted to say that. So K and L are the parameters that will follow me also. Then to check conformal invariance, you do the inverse, the conformal inversion, and this is how the integral behaves. Now, due to that, the integrals can have this form, and they depend only on the two cross ratios, as it is well known, of U and V. So the basic non-trivial function is this phi with the parameters L and K of U and V. And now you can do the conformal transformation, fixing the conformal frame. You send one point to infinity, one to 0, one to 1, and another to the z. And so now the function, the integral takes this form. So the function of interest is this phi of the two variables z and z bar. This is actually two real variables, but I write them in terms of z and z bar. Okay, I think one of the very interesting works in this direction was done by Isaev in 2003. which gave a very nice integral representation for these integrals for any loop L and any depth, as I will call it, K, which means any dimension in language, by a formula like that. So that's an integral formula.
May I interrupt? Just because I'm a little bit lost. You are in 2K plus 2 dimensions
exactly.
of the space.
Exactly.
All right. But now, what is the Z and Z bar parameter?
Z and Z bar are related to the points x1, x2, x3 because they are the
these are the two special points that you are.
Exactly.
Okay. The rest is when you have the limiting procedure.
Exactly.
Okay,
Yes.
good.
So one of the points x1 goes to zeta. So this is zeta, not z yet.
Yes.
The other goes to infinity. The other goes to 1. So these two parameters u and v, they become actually zeta and zeta bar, functions of zeta and zeta bar. I didn't write it here.
Okay.
So so essentially the 4-point function depends on two parameters, That's the conformal magic. And it has an integral representation, and this non-trivial function of zeta and zeta bar has this nice representation that we found by a very simple change of variables. Anyway, you keep this. This is a very nice integral representation. If you have photographic memory, you will see it in a few slides later. It looks complicated, but we think it's interesting. And this thing D0K, I write it here. And for K equals 0, I define it as something that you would again see. So this 0K is interesting and important. Okay, right. So now, what is the observation that we did? The observation we did is that we can reproduce this result by a completely different method or system, which is surprising and perhaps deep. What is this different system that produces the previous result? Which I hope you understood, it's really a result of calculations and a lot of effort by many people over decades. So this simple system is a quantum mechanical system that consists of two harmonic oscillators where they have common frequency, which I denote by M, because it plays the role of a mass, as you will see. And the mass of these oscillators, the actual mass, is 1. Now, these oscillators interact through an imaginary chemical potential, you can call it, or you can view it as an imaginary homogeneous constant magnetic field along the third direction, because this P2x1 minus P1x2 is nothing but L3 in the third direction. So this model has many incarnations. You can view it physically as, in many interesting and different ways, but it's a very simple quantum mechanical model. Now, this model can be viewed as a deformation of the free particle, which is just this free particle, by two operators. This is one operator, O, and this is the other operator, Q, which is essentially the angular momentum. And the deformation parameters are M and N. So now if I do some reshuffling of the creation and annihilation operators, etc., the Hamiltonian takes this diagonal form. H0 is the free Hamiltonian. MO is the deformation by M squared. And if you use this number operators, it's like that. And actually Q, which is the deformation by this operator, is N1 minus N2. So it's nicely disentangled. There's a diagonal form. And so that allows to calculate the partition function in a very easy way. And now I write the partition function in terms of this Z variable, not zeta, Z, which is exactly this very kind of familiar looking variable, E minus beta M minus I beta mu. So now the partition function is written in terms of this Z variable. Now, some technical stuff which we cannot avoid. Let's define a differential operator. I want to take the derivative with respect to M squared. Or the
in the previous transparency, the Hamiltonian, once you add this term, it's not significant, but this one seems to be significant.
It has an I in front.
Yes, but this one seems to be significant.
Sorry. Hamiltonian is this. All.
Or in the previous, let's say in the first one, the one before Q. That one.
There's no
the previous one.
previous one.
Yeah, that one, because of the I, is not.
Yes.
But the rewriting it seems to be significant.
What?
Just the diagonal.
There is an I, so that's why I.
So
I'm showing you this is a okay. Yeah. So it's an I of beta mu.
So the full is
The full is this one, yeah. So I said it's like a deformation by m square O minus I beta mu q. So yeah, it has this I. It's like having an imaginary magnetic field coupled to. So okay, these two operators are which are the derivatives with respect to the two deformation parameters, m square and mu, and I write it in terms of these variables z and z bar, and they have this interesting form. They commute, and now if I use these derivatives, I can calculate the expectation value of maybe some piece of software. I calculate the thermal one-point functions. It's a kind of easy exercise for students of maybe high school, something like that. It's really a game. But and I write it in this interesting forms. And I notice that if I want to use high mathematics, these are called Poisson kernels for harmonic functions that have a constant boundary value at a single point of the boundary, which is either the unit circle in the first case or the upper half plane in the second case. So in another way, again, it's like bulk to boundary propagators in Euclidean ADS2, but with different coordinate systems. The same propagator. The first one is given in Poincare coordinates. The second one, if you write ADS2 in upper half coordinates. Global coordinates, the first one, and the second is in Poincare coordinates. So it's an observation. I don't think it has been done, but okay, it's yes.
Sorry, usually the boundary propagator is like the two-point function, right? Why is this like related to the one-point function? Here you said that.
This is one-point function of another system. It's a completely different system. This is the bulk to boundary propagator. This is the mathematical form of the bulk to boundary propagator of a field, massive scalar field in ADS2. This is what it is. I give it a completely different interpretation. This has nothing to do with ADS2. On the left-hand side, you have a thermal one-point function of a quantum mechanical system. No, there's no ADS2 here. It's just quantum mechanics. But it is this form and this form are bulk to boundary propagators of ADS2.
Sure, but the ADS2 propagators, you can interpret them in terms of ADS2 CSV.
Yes, well.
Right? And then the question there would be, is there a relation between this one-point function and the two-point function?
This is a question that I don't know because we are still discovering. Yeah, I don't know why this is correct. This is, of course, a very interesting question. I have it in my outlook. But at the moment, it's an observation. I'm not going into ADS2 at the moment. I just observe that this is what happens.
So O is a quadratic operator in the x's, right?
O?
O and Q.
Yes, x squared. Yes, x1 square, x2 square. This is also a quadratic, well, P and x. Yes. So, but yes.
You use the letter Z to remind us that this is some sort of a chemical, like a fugacity.
This is like an imaginary fugacity, yes, exactly. But I use it
Are you going to talk about Li Yang or not?
No.
No.
No. Unfortunately, no. I had papers in the past about Li Yang, but not now. So it's kind of reminiscent of many things. What draws me to this research direction is that I see many connections to many things. Remember, I talked to you about conformal integrals. Now I'm talking to you about quantum mechanics. Now I'm taking another step. I use this quantum mechanical partition function, which is for high school students, to calculate the partition function or the free energy of an ideal gas. How would I do that? If I integrate over a relativistic density of states, I give you the relativistic density of states in d dimensions. What are these d dimensions? Maybe I did not write it here explicitly. The d dimensions, and I'm sorry for that, I didn't write this explicitly, it's in the next step. The d dimensions are hidden in this L. I'm sorry for that. This rho of L is the relativistic density of states in d, small d, equals 2L plus 1 dimensions, in odd dimensions. And if I integrate this density of states with the partition function, the free energy I showed you before, I get the free energy of a system in d equals 2L plus 1 dimension. And this is the integral. This is the integral, the second line. And if you remember with your photographic memory 3 slides ago, this is exactly like the integral of Isai. Exactly. So now, okay, these are technical stuff. So this free energy here, that depends on the parameters z and z bar, and this geometric parameter alpha, which, okay, I can explain if I'm asked later. It has this for, so this is a function of z and z bar. Okay, let's do that. And what is this function? It's been calculated. It is written in terms of a finite sum of polylogs. This is a single valued polylogs. L, again, I'm sorry for that, is related to the dimension of the system. So I have an ideal gas in a number of dimensions, which is odd, and it's related to this L, but L is the loop of the integral. There's nothing to do with the dimension where I do the integral, which was this K. It's a different thing. I will make it a different system. It's a different system. Anyway, special cases, n equals 0 is the free energy of the harmonic oscillator, and when m and mu are 0, which means z equals 1, this guy becomes the zeta function in 2L plus 1 dimension, in odd dimension. So these are single valued polynomials. Okay. So now this is where D appears, finally. So I am going to relate the previous result. I will claim that it's exactly the same as the following thing. Now I'm doing quantum field theory. I take a system, massive, free, complex scale. This is the Euclidean action. Of course, I include an imaginary chemical potential or an external gauge field, as you want to call it. I calculate the partition function. And the key result is that this path integral calculation, which again can be done in your quantum field theory class, is exactly the result that I showed you before, which is this polylogarithmic function, exactly this. When I make the identification that the geometric parameter is actually a ratio of the spatial volume, which I need to regularize at some point, because it's an infinite volume, but as usual I regularize it, over beta to this thing. So if I take this identification, these two formulas are exactly the same. Okay. Right, so we have two things that are, they look the same, and now we can play some mathematics with that. We'll see how, with time, that's okay. Right, what we notice now? We start noticing a few things. If I have the free energy or the partition function of this quantum field theoretical system, I can act with my D operator and obtain the one-point function, the thermal one-point function of my operator O or my operator Q. Basically, this is phi squared or the charge operator or a U1 charge operator. And I can do that. So I do an explicit relation, but I notice a recursive relation or recurrence relation like that. I act with D on logarithm of ZL, and I obtain logarithm of ZL L minus 1. I act with LZ here, and I go to L plus 1. So these functions that I showed you before, the polylogs, they obey some recursive relation or upon acting with this differential operator. There is another operator that I want to use. It's an integral operator that has properties. It commutes basically with this big D and big L operators. Which is this integral operator is interesting because I can, pack everything into a better language. I use this integral operator in this way, and I do some ordered integration, which is called iterated integration in mathematics language, and I obtain the free energy of the system in L dimensions, let me use L from now on, from the quantum harmonic oscillator. I integrate many times in a correct way, and I obtain this result. Mathematical observation. Another mathematical observation is that if I act with this differential operator on the harmonic oscillator free energy, I obtain this guy here, which I rewrite it again. Now, what is this guy? This later guy. It's related, first of all, to a massless propagator of a scalar field with scaling dimension d over 2 minus 1 in d dimensions. So I can think about it as related to some field propagating in big D dimensions. That is the right scaling dimension. But on the other hand, this is the bulk to boundary ADS2 propagator for a scalar with a mass k minus 1. This is exactly what it is. And my operator is what they call, some people, mass shifting or dimension shifting operator of the bulk to boundary propagators. It's exactly what it is. If I act with this guy here, I shift k by 1, and I will show it to you in the next, exactly in the next transparency. So I act with this guy here on the thing that I showed you before, and it goes to the same thing with k plus 1. This is called mass shifting or dimension shifting operators in ADS CFT. It has not been done in ADS2. It's a very simple, again, observation. That it has nothing to do with what we were trying to do. Now we will try to do this as well, to understand this as well. So there is an operator which I define like that, shifts the parameter k, which I call depth. I call this parameter depth. And this operator, this log zk, also commutes with the integral operator. So what is the finally I can shift starting from the harmonic oscillator, just from the simple harmonic oscillator, and I reproduce this function d0k, which has, as we discussed, two lives. It can be either the two-point function of a massless field in big D dimensions, or a bulk-to-boundary propagator in 2 dimensions, but of a field with mass related to k. Okay, this sounds a little bit confusing, so let me kind of summarize for a moment what we did, because we were also confused finding all these expressions, and at some point we have to put them in order. So that's the first line is the partition function of the harmonic oscillator. The second line is the free energy, basically, of a system in L dimensions. The third line is what I call the bulk-to-boundary propagator of a field with mass k minus 1, or simply this function. I will have a list of differential operators, integrals, an integral operator here in the last line, and we have the commutation relation. So we have results like that. We have recurrence relations here, etc., etc. Okay, that's maybe not important, but it's useful to be shown. So what is the main result? The main result, the main mathematical or observational result is that the conformal integrals that I showed you before in the variable zeta and zeta bar are exactly equal to these functions d, l, k in the variable z and z bar if I make this identification that zeta, which was a space-time point, or actually a conformal ratio, is related to this z, and when g, which was the conformal coupling, because in conformal theory we have a conformal coupling, is related to this alpha square. If I make these two identifications, the results are the same. And this is not so trivial, because you may have seen that the results are complicated polylogarithmic functions. So, okay, it's an observation. We still don't understand why, and that's what we want to understand a little bit. Now, another equivalently nice result is that this phi non-trivial function of the conformal integrals can be written in terms of these d functions in this nice interesting ratio. And we noticed, and this is we thought we made a mistake in the beginning, but actually it is not. There is a 1 over L factorial here that connects the two things. So there's 1 over L factorial here. You can see 1 over L factorial, which apparently is a kind of intriguing also as well. Now, one first thing that one notices is that in the conformal theory, the coupling usually in the perturbative calculation has to be taken small. But if I make this identification, the coupling to this parameter alpha square, it means that alpha square must be small, but alpha square has beta, which is the inverse temperature in the denominator, so the temperature is the numerator, so the temperature has to be small. So this corresponds to a kind of low temperature expansion, is my theory. So perturbative in G means maybe non-perturbative in this language, but still this to be understood. But it is definitely a low temperature expansion.
So what was alpha again?
Alpha was the ratio between, well, it was a kind of geometric parameter, but eventually it's the ratio that I have it here, between your regularized volume and beta, where it's the inverse temperature. So if you think that the regularized volume is a large thing, beta has to be very large also, so small temperature. Again, this is something that reminds us of other correspondences, but let's not go this direction. So this is a picture of what we have managed to put in place. We just start with this free energy of this quantum mechanical system. And we act with these operators, actually with two operators, with LZ. We go in the right direction. We act with the integral operator, we go in this direction. And because they commute, we can reach every point in this diagram by any way we want. Now, L here, if you use it as a loop parameter, goes like that. Zero loop is the first line, etc. But it's related to little d, which is the dimension of the quantum mechanical system. And k here, again, you can view it as what we call the depth parameter, or the integral, the dimension of the integrals. So these are things. Okay, now try to understand this relation a little bit more by a brute force calculation. It's not, which is not so complicated, but it is there. All our functions d, l, k satisfy a second order equation, which is kind of intriguing if you write it in terms of both the z variables, but also the original m and nu variable. So this is the usual Laplacian, and these are some other terms. We still don't have an interpretation of this equation. It's a function. These are functions, polylogarithmic functions, and actually it looks like an eigenvalue equation. The eigenvalues are L and K.
This was fixed by trial and error, or
This was fixed by trial and error at the moment. We think it's related to some Casimir of some symmetry, probably SL2R, but etc. But we haven't done that. You know, it was the very last moment we checked it. The only thing we can do very easily is to say, for L equals 0, which means D equal 1, that means when I am at the level of the harmonic oscillator, this looks like a scalar field of Euclidean ADS2 with this global metric with a mass, as I promised to you, k minus 1. So that's what the bulk to boundary propagator of ADS2 satisfies. But that's for L equals 0. We don't know what happens when we increase L. That's one thing. Okay, now, so now this is the part that actually started the whole, our whole investigation. Our work started when we noticed that these functions appear when we were trying to study thermal two-point functions. That's another big story, which is very interesting and actually is gaining attention in recent years, actually also in this year. You know, I could have continued without mentioning the story, but actually this is what started the whole story. It is very interesting to study thermal correlators both in conformal field theory and in general quantum field theory. So if I wanted to study thermal correlators in a quantum field theory, they have a fixed form, and the only non-trivial things are these coefficients here, A, which are the subject of investigation using bootstrap techniques or analytic techniques or numerical techniques in recent times, actually this year also. But these other terms, which is the Gegenbauer polynomial and some powers, are the so-called thermal conformal blocks. Now, what we did some years ago is to study these two-point functions in a massive CFT, not because it is conformal, but because we can calculate this thermal two-point function, and it has this form, an infinite expansion. And the observation is that these coefficients here, which depend on the parameter z and z bar, that I just showed you before, are related to the functions that I showed you before in this way. So the only things that were related to the functions that I showed you way, however, are two of these infinite coefficients. It is the coefficient that corresponds to the contribution of the scalar field, and it's related to these guys here, the L minus 1, 0, 0, k equals 0 in this case. And the coefficient which is the contribution of the spin 1 operator or U1 charge operator, which is related to the k equal 1 field only, but at every loop. Okay, thank you. So the story is the following, that although we know, as I will actually show you, I should say this, I go on to transparency. Although we know the full result for this OPE coefficient, and it is given by this, again, sum of polylogs with a single value. We were not, this is the contribution of higher spin operators in this operator for the thermal two-point function. But this does not contribute, this is not directly related to conformal integrals. Only the spin 0 and spin 1 guys are related to conformal integrals, as I showed you. What about the higher spin operators? How are they related, if they are related to conformal integrals? What we found is that they are related to recursive relations. For example, the one-point function, the thermal one-point function of the spin S plus 0 guy in L dimensions is related to the spin S guy in L plus 1 dimensions and to the spin S guy in L dimensions. So eventually, if this is the spin and this is the dimension, we can, for example, here, L equal 1 means 3 dimensions, spin 2 is the stress energy tensor of a 3-dimensional theory. This is related to the spin 0 guy in the 3-dimensional theory plus the spin 0 guy in the 5-dimensional theory, etc., etc. So all the higher spin one-point functions are related recursively to the lower spin thermal one-point functions, which are related to conformal integrals. So indeed, the conformal integrals we studied form a basis for studying the thermal one-point functions of all thermal theories, massive thermal theories, massive thermal theories. The final thing that I want to say is the following. We had a crazy idea, because we could do it, is to consider the so-called hyperpartition function, which means take the partition function and sum over all dimensions. So it's like it's a little bit crazy to have a partition function of a system in 1 dimension, harmonic oscillator, 3 dimension, 5 dimension, etc., etc., and kind of multiply them or add the free energies. It's the same thing. Why you should do that? Consider a system in 27 dimensions. But dimensions correspond to loops. So if I do that, is equivalently to adding the loops. And lo and behold, we can do that. So considering this hyperpartition function, which is the product of the partition function, and the hyper free energy essentially, it looks like we can calculate it. And actually very easily, because it obeys a first order equation, which I write it here in 2 equivalent forms, which can be integrated. So we do that, and it corresponds now in the language of integrals to sum an infinite number of integrals for all loops. And we do that, and it's an interesting result, blah, blah, blah. And we can do that for all dimensions, all k's, but for k equal 1 corresponds to the d equal 4 result, the old result of Broadcast and Kapodistrian, which is given by a very beautiful integral of a Bessel, 0 Bessel function. So, we gain something, although this is not a new result, but we gain some intuition, some leverage by considering this kind of things. Okay, so the extra material that I had is that the main puzzle that we had for a couple of years is that our result has, as you can see here, a sum and a difference, or a real and imaginary part of the polylog, depending on this S. So if I want to consider one-point function of a spin 1 guy, this is a minus. And everywhere you ask in the business of calculating multi-loop integrals, they all find integrals which involve the imaginary part of the polylogs. Asking the experts for a few years if they have found integrals that involve the sum of the polylogs, nobody knew. He actually asked many people in person and by email. Nobody had the result. But at some point somebody told us, well, maybe this is related to d equal 2 dimensions. And we did the calculation, and actually, indeed, it corresponds to the so-called Fishnet model in d equal 2 dimensions. But the Fishnet model has this form, like that, and in d equal 2 dimensions, the number 1, is very singular. It's like a two-dimensional theory where one of the two fields basically does not propagate, because actually this kinetic term becomes constant. But you can take the limit, you can take out the limit, you can subtract the singularity, and the resulting finite result is exactly the polylog with the plus. And that was for us a big step to continue our discussion. That is why we have the results for all k. Okay. Right. So this is what I'm saying here. Thank you. I will be actually even ahead of time because I'm finishing. So this is the result that we have. The Fishnet integrals, okay, arise if you consider 4-point functions of this model for large L, the leading NC contribution, etc. So to take the d equal to limit, you have actually to renormalize a little bit the coupling constant by this thing that diverges. So the discovery was that the free energies of massive field theories in L dimensions are related to the 4-point functions of the Fishnet model in 2 dimensions. That was the thing that matched everything together. It looks like a technicality now, but I can tell you that it was a surprise even to people like Kazakov, who did this for a life. They could not understand. They noticed it. They knew they had them in their calculations, not in this form. But then they realized that starting from the 2-dimensional Fishnet model, you can go to the 4-dimensional Fishnet model by just a differential operator. Just one taking the derivative of the 4-dimensional case, you go to the 2-dimensional case. It's very simple. Then you can go actually to the 6-dimensional case, etc., etc. But the 2-dimensional case is singular, and you need to be a little bit careful. Okay. So this is the summary of something which I understand is I don't want to say chaotic, but it looks complicated because we think it has many legs in different directions. So the summary is that from one side we have this conformal other integrals which live in d dimensions. They have a loop order. They have 4 or 3 space-time points in this conformal frame. They have a dimensionless coupling. And on the other hand, we have this thermal 1-point function, which have a so-called depth, which is an integer parameter related to the dimension 2k plus 2. They have a dimension, which is the dimension of the underlying quantum mechanical system, which is odd, and it is related to the loop order like that. Well, they have a mass and a chemical potential, which is related to the z parameter, and they have a geometric parameter, which is related to the coupling like that. So that's the kind of Hertzsprung-Russell diagram of what is happening, astrophysics, Hertzsprung-Russell, etc. So we are doing observational things at the moment. We try to put things in order and perhaps ask the more fundamental questions now at the next level. So that's my ultimate transparency. So, of course, there are interesting questions and that we ask and many people ask regarding our work. One deep observation is that this looks like AGT conjecture. It's Aldai, Gayoto, Tajikawa conjecture, where conformal 4-point functions of a 2-dimensional theory, of a UV theory, or conformal blocks equivalently, are related to partition functions of a quantum field theory, essentially are related to the Nekrasov partition function. And the identification in that case is very much like ours. You identify the space-time points in 2 dimensions to the moduli of the instantons of the 4-dimensional theory. The moduli have this form e to the minus beta something, etc., and they are related to the conformal ratio. So this looks very much in this language, but without all the supersymmetries and without all the mathematics at the moment. Large charge expansion, the resummation of these ladder integrals, and as I say, it's my last transparency, so I think I'm on time. The resummation of this large charge, the resummation of these loop integrals have appeared in recent works. I mentioned one of them in large charge expansions. In the thermal bootstrap, because they are related to thermal one-point functions, the thermal bootstrap, one fundamental question is how conditions like the KMS constrain this thermal one-point function. So it is an interesting question to see whether these integrals obey some sort of KMS modular invariance. And again, you can somehow see that there is something there. Okay, I mentioned the modular properties of these things, connected to string amplitudes and integrated correlators. Now, one thing that we are doing at the moment is to discuss higher derivative field theories, which are related to long-range critical systems. And we can do that. So we can generalize our results to higher derivative theories. Again, interesting way of getting fun. This is connected to integrability. Recent works they have shown using our results actually, so that these integrals obey some sort of total-like equations. And finally, maybe, probably, this is related to ADS2 CFT1 correspondence, and a recent work studied that by Hartmann et al. So, thank you very much.
Let's see if this works. Thank you very much, Tasso, for the nice talk. So, questions, remarks?
So, these simple valued polylogarithms that you encountered in these ladder integrals, so a basic property that analytic properties that they only have isolated singularities and no branch cuts. So in these zetas or z variables. So this is understood in the side of the integrals. Is there a physical interpretation in the side of the quantum mechanical system or the quantum field theory?
No, I think that's a very interesting question. Not yet. What people do in studying thermal one-point functions, basically what people do studying thermal two-point functions, which are expanded in thermal one-point functions, they study the modular properties of the thermal correlator, and they try to use them to constrain the one-point functions. So we think that the single value properties of these results are related to modular properties of the corresponding thermal system, because this is what you have. This is the only game, the only property you have to exploit in the thermal system. You have a kind of modular property and some analytic behavior of your two-point function, of your thermal two-point function. You see, the integrals are one-point functions, so you can see them as a basis in which you expand your two-point function, which is very similar to what people do in conformal integrals. They use the single-valued polylogs as a basis, as you know very well, to express multi-loop integrals. Is that correct? Okay. So this is a similar game we think is played in the thermal case. You want to calculate thermal two-point function, and you want to expand it in this thermal one-point functions. And these one-point functions are these single-valued polynomials, we think. So the two-point function has a modular property, which integrals must be expressed into this one-point function. So that's the thing that it comes to my mind, but it hasn't been studied.
And the modulus is related to the temperature, or so modulus has to do with some parameter, inverting some parameter or something of the sort. So
KMS conclusion is the fact that your two-point function is periodic in beta direction.
So yeah, has to do with the
But
temperature.
there is also an inverse. It's not only the periodicity. Probably you need also kind of inversion of temperature. This is under investigation in many cases. They do that in the thermal bootstrap. And, okay, it's interesting to notice that how it appears in the terms of the correlation of the integrals.
Thank you very much.
Thank you. Yes.
You mentioned that your conformal ladder integrals are in even dimensions, capital D is to k plus 2. From your alternative expression in terms of polylogarithms, can you analytically continue to the odd dimensions?
So the dimensions of the integrals are related to the loops. So
Right.
the general expression is like that. So L here is an index in the polylog. L is an index in the polylog, and actually this number here S.
Directly is asking also why you don't consider probably odd integrals.
Yeah, I'm asking about the parameter k. I think capital D is to k plus 2.
Yes, yes.
I'm asking about this k.
K
or
is
the capital D that
yes.
you mentioned in one of your last slides.
So K is related to the spin of in this case. K is related to the spin,
I see.
but not in a direct way. Not in a direct way. K is related to the spin. Indeed, yeah. I think if you ask this question, I think the answer is this one. This guy here, for this guy K is 0. For this guy, which is spin 1, K is 1. We thought that it would go like that. That after spin 2, we have K equal to, which means 6 dimensions, but it doesn't go like that. It goes only for spin 0. This is D equal K equal 0, D equal 1. Okay. It doesn't go like that, but it is related to the spin. So higher spin in the thermal star corresponds to higher dimensional integrals, but combination of these integrals with a recursive relation.
Thank you.
May I ask a question?
Yes, Mari.
So, if I understood correctly, there is, between this L and K, I got the feeling that you have a sort of duality between a system, between a sort of duality where on the one hand you have the dimension, and on the other hand you have the loop. Now the loops, say, there is a parameter which is naturally associated with them, is the h bar. So there is fine. What is the parameter which would be associated therefore to the dimension?
I think that is a very good question. I don't have a good answer for that, but I think it's a valid question. I'm inclined to say that it has to do with geometry of like genus expansion.
Yes, but but this is this is our full background, right? So because this is the only thing we know, but genus doesn't change the dimension.
Yeah. So if you want the more radical thing is to say that when we talk about dimension in a quantum field theory, this is not necessarily related to the dimension of space-time.
Okay, you have an interaction that play a role, and how much is the how do you say the correlation?
Yeah. So.
Dimension, yes.
But to be discussed.
If you don't mind, I have a question of my own. I was wondering, I hope you can answer it fast. I was wondering if the original observation that the conformal integrals are related to these two-dimensional harmonic oscillators, isotropic, with the extra term proportion to L3, including the I. We know that the isotropic harmonic oscillator has an enhanced SU2 symmetry. Putting the I perhaps makes it SL2R, and I was wondering if this is the SL2R that you have to have it in the conformal integrals, and that's how.
Exactly.
So
I think you are absolute. I think you are right. I think these differential equations that we also find must be related to SL2R. It has not been noticed. Actually, ADS2 people study SL2R. So yeah, there must be some SL2R symmetry behind that. But people who do conformal integrals, they don't know anything about SL2R.
Thank you very much. So let's thank Tassos again. We have other slides on. These slides are here. No, you don't. Okay, for those of you who have been long coming in this series, we have different subjects and we like to mix them so that everybody is obliged to attend everybody else's talk. Okay, so we're very happy to have John Seuss here from Yale and ESI talking about bipolaronic high transition temperature superconductivity.
Thank you. So I want to thank the organizers. I want to thank Eris and all the organizers for inviting me. It's great to be here. And before I start, I'm an assistant professor at Yale in applied physics. Yes, have a lot of and, we're looking for. So if you have good students here in Greece, please, and if they want to go abroad, please send them. Okay, so that would be great. And today I want to, so let me give you a very fast spiel about what I work on. I'm a condensed matter theorist, so hopefully I'll be able to make a broad introduction to this topic that I understand there's a lot of folks here from high energy that I hope that they can appreciate the topic I also work on statistical physics of neural networks and classical systems, but I'm not going to talk about this today. So the topic is about a new mechanism of high transition temperature superconductivity. This work was started actually when I was a student at UBC with those folks. Then I moved on to Columbia as a postdoc, and I did some work at Columbia, and then with these collaborators, and then those two students at Stanford who moved on to different postdoc positions. All right, so let me preface the talk by telling you that the mechanism is about electron-phonon coupling. So I don't want to discuss any exotic superconductivity from correlations, from electron-electron repulsion, or electron-electron attraction, which is in a sense trivial. I will talk about electron-phonon coupling. So phonons are the vibrations of the crystal, and if you took a graduate course in condensed matter during your studies, you most certainly have heard of something like this, and you heard that it's boring. So the goal here is to disprove that argument, because in the recent times there's a lot of recent results that strongly violate this intuition. So here's my outline. I will discuss first the weak coupling theory of superconductivity. That's what you'll learn in a graduate course. I'll review quickly BCS theory, then I will discuss what is known as Migdal-Eliashberg theory, which is an attempt to go to strong coupling. It's a one-loop calculation. It fails, but it accomplishes some things. In particular, we can empirically bound the critical temperature below which superconductivity emerges to 1/10 of the phonon frequency. Omega is the phonon frequency. And actually this bound is to some degree found in conventional superconductors. Conventional superconductors are those that are described by weak coupling electron-phonon superconductivity. Then I'll move to strong coupling, and I'll discuss something that I call the density coupled models, which basically is the basis for why we get low TC in all these previous models. Then I will discuss new types of models that I worked on, which have hopping modulation instead of density coupling. And this will lead to the two mechanisms, bipolar high temperature superconductivity, and then we'll even prove that this is robust to Coulomb interaction. Okay, so let's start with weak coupling superconductivity and BCS theory. So this is very simple. The idea is, in a solid, at low temperatures, we have fluctuations of the lattice. So these fluctuations are what become the phonons, and any weak electron-phonon interaction in a metal at sufficiently low temperature will cause an attraction. It will cause, we call this the phonon glue, colloquially, and it will cause an instability of the Fermi liquid. We get a new state, which is a superconductor, which is basically a superfluid with macroscopic occupation of pairs and has a pairing gap delta. So the presence of a gap is very important to protect superconductivity, and we expect generically, at least in normal metals, that this will happen at sufficiently low temperature. Okay, so this is very well understood. It's universal. We understand a lot about it. You can read about it in textbooks. It's a very beautiful theory. And now, of course, normally you would say, well, if the electron-phonon coupling is very small, then what happens when the electron-phonon coupling becomes stronger, right? The phonon is the glue. So if the glue is getting stronger, does that help with superconductivity? So Migdal and Eliashberg looked at this, and this is basically their theory. It's a one-loop calculation. They just have the rainbow diagram and a bubble, and the idea is that you can do an expansion in real materials in omega, the phonon energy scale, or the phonon frequency, over EF, the Fermi energy. That's because in a real solid, ions have very low energy. The ion motion or the ion vibrations are low energy because the ions are much heavier than the electrons. So this is naturally a small parameter. You can do this expansion in lambda omega over EF. Lambda is the dimensionless, the bare dimensionless electron-phonon coupling. And if you do this expansion, you neglect vertex corrections, and you arrive at those two diagrams, and then you can solve for the superconducting transition temperature. The issue, of course, is that this is really not strong coupling, because if you go to sufficiently strong coupling, there are effects due to the neglection of the vertex corrections that you will miss. For example, you will miss the formation of polynons. And that's been documented in various papers by various authors. And the point is, well, when polynons form, I have not defined what those are, but when polynons form, these quasi-particles they tend to form in pairs. That's why we call them bipolarones. And when they form, they're very bad for superconductivity. I also haven't defined why, but that's kind of the general dogma in the field. So that means that if I want to empirically bound TC, all what I need to do is use this formalism until the value of lambda at which bipolarones emerge. Then I know superconductivity will be quenched, and this will be the best TC I can get. So this way I maximize for TC. So you can do this with various techniques, numerically, not numerically, empirically, whatever. In the end, you get this bound. The TC is about 1/10 of omega, the phonon frequency, or is upper bounded by 1/10 of the phonon frequency. This is not a mathematical bound. You can have violations. It's just an empirical bound that in this class of systems, which apply to presumably a lot of materials, TC can be at most 1/10 of the phonon frequency. So of course that's why we get low TC in real life, because the phonon frequency in materials is not an arbitrary number, right? It's something like 0.03 electron volts or 300 Kelvin. So 1/10 of 300 Kelvin is 30 Kelvin. So that's why conventional superconductivity is 30 Kelvin. And that's what people thought about superconductivity for a long time, until maybe mid-80s, when, or like mid to late 80s, when the cube-crate high-temperature superconductivities were discovered, and they led to the belief that we actually can get better than this. And there are now many examples of high-temperature superconductors, and they're widely debated. They may or may not be universal, and so forth and so on, right? So this is just trying to tell you that this is not the full story, right? This is a big part of the story. Yes?
So this, when you say that the paradigm changed and the tendency changed, is it because of the different universality class, or because even in this one we discovered that this bound could be violated?
So I don't think it's a universality class. I think this theory is universal when it applies. It just doesn't apply to every material. The microscopic sometimes are important. So that's basically what I would say. Does that answer your question?
Does 1/10 come from the exponential factor? I mean,
You take the exponential and then you expand it, right? And you bound at the lambda. Lambda's order 1.
Okay.
So
that's
you
what get that. Okay.
Yeah, but you can do it numerically too. So the other people like Kevelson more recently did it numerically. They just do Monte Carlo, exact Monte Carlo. They do Migdal-Yazbek, and then they see TC drops when Migdal-Yazbek is not good, right? So then you see that this happens around 10th of omega.
It doesn't do that with stripes, right?
No. Just normal standard so-called Holstein model, what I'm calling density coupling in my talk.
May I ask you, can you give an argument why formation of bipolars is so decisive channel, like the clusters of polaroids or other processes dominating superconductivity in neutron?
Okay, yeah, this is a great question. So I was going to come to this, but basically the idea, I think also that answers your question, it is when the coupling becomes strong, vertex directions become important, and it's not included in that theory. So what happens in real life are one of two things. Either the coupling becomes so strong, the crystal, the real crystal in real life becomes unstable, and there's a structural transition. We get a whole new crystal with a small electron phonon coupling, like it renormalizes itself, hence you cannot think about these things. Or if that doesn't happen, one of two things happen. You form bipolarones, and these bipolarones are heavy, so they quench superconductivity. And these bipolarones, if you're at low density, they can form a fluid, but with, it's not really, if superconductivity could exist, it would be very, very low TC, or they form a charge density. They form basically some sort of state that breaks transitional symmetry that has charge ordering. All of the above are interesting, but they're not high temperature superconductivity. Does that answer your question? Okay. All right, so I appreciate that people are interested in this, but I haven't said really, I said just right now why bipolarones are bad, but I really didn't define them, so let me define them. So what polarones and bipolarones, this is the blue sky view of polarones and bipolarones, so forgive me for being a little bit colloquial, but the idea is very simple. If I have an electron moving in a crystal, just a single electron moving in a crystal, and there are phonons, then these fluctuations of the phonons can induce the formation of a bound state of the electron with the cloud of phonons. The cloud of phonons is the magenta region you see here, and we call this quasi-particle or this object the polaron, right? And this is a topic that was actually very trendy in theoretical physics in the early days. Landau, Picard, Feynman, many others worked on this problem. And of course, if we have now two of those objects, right, they can exchange these fluctuations, they can exchange the phonons and lower their energy, so they form a bound state of the two polarons, which we call the bipolar. And the conventional wisdom is, again, this is sort of a very colloquial argument. The conventional wisdom is the electron is moving in the crystal, so if it wants to move and it's bound to the phonons, which come from the heavy ions, it wants to carry these phonons on its back that tend to be very hard, right? This is very classical argument. I'll give a better argument in a few slides. So that means that this object, this polaron, will be very, very heavy. You think about it as a heavy elephant. Now we have two of these objects, and they're exchanging phonons, so they're going to be even heavier, right, if they form a bound state. So, a much heavier bi-elephant, or whatever you want to call it. Okay, and why is that bad for superconductivity? At the intuitive level, it's bad because it's quenching the kinetic energy. But if you want to be precise, well, if these things are going to form a superconductor, they're bosons, so they're going to form a BEC of bosons, and TC scales as the density to the 2/3 in three dimensions over the mass of the bosons. The mass becomes very small because these have been now bound and localized in a matter of fact in the crystal, so TC will be quenched. So that's basically why bipolarons are a bad story for high temperature superconductivity, or that's at least the view before these works I will talk about right now. Okay, so hopefully now you have an appreciation of what superconductivity means if you've never heard about it before, but I'm certain you have. And the beautiful attempts to go to strong coupling, but it's not strong enough from my point of view. So I'm going to even go to stronger coupling. So the motivation philosophically is if I want to go to even stronger coupling, and particularly I'm going to think about two limits at the same time, right? I'm going to think about either very strong coupling and very low density of the electronic system. If I have very low density of the electronic system, then I can't really think of a Fermi liquid as a good starting point. So this one loop calculation may not even be valid, not just because I'm going to strong coupling and the vertex corrections are important, but also because if I'm at very low density, I don't have a Fermi surface, I don't have a Fermi liquid, I can't really do an expansion around the Fermi liquid. I need a very different type of framework to start with, right? Omega over EF, in other words, if I want to put it in numbers, omega over EF is not much smaller than 1, because EF is controlled, Fermi energy is controlled by the density. My density is becoming very small, so I no longer can guarantee that this is a small number. Okay, so that's the limit I will think about in this talk. And here I want to highlight two things. Maybe if you will remember those two things when you go home, that would be great. That's all what I'm asking of you, is that I will have strong coupling / low density limit, and that I will discuss some particular mechanism of the coupling between the electrons and the phonons that have different names in different communities. I will discuss all of them, but the most descriptive is to call it a hopping modulated coupling. It's a coupling that from the phonons that modulates the hopping of the electrons, modulates the kinetic energy of the electrons. Okay, good. So let's start with the stories. Going back to bipolarons, why they're heavy, and let's try to give a more convincing argument instead of this picture of just heavy elephants. Why they're really heavy? So the reason they're heavy is based on what I'm calling the density coupling, as opposed to the hopping modulated couplings. The density coupling means I'm coupling the lattice, which is X, the displacement operator that I have in my crystal, the phonon, to Ni. This is Ci dagger Ci. This is the charge density. That's why I call it density coupling, right? If you know more condensed matter, this is known as the Holstein model, right? Which Holstein wrote in the 40s, right? And there are other models like the Frulich model, but basically many of these conventional models are cousins of this model, right? The charge of the electrons, the density of electrons is modulated by the vibrations of the crystal. Pictorially, this is a sensible model for the following reason. Imagine I have a molecular crystal, and this is my unit cell. So every periodically repeating unit in my crystal is formed of a molecule. I am representing the molecule by a dipole here, this orange and blue dots connected with a spring. And then I have deformations with the spring because I add electronic states or I remove electronic states, whatever. So this deformation of the spring means that I have a harmonic oscillator where the spring sits, where the molecule sits. So that naturally means that this coupling is a very sensible thing, because what's happening is the vibrations are modulating the potential locally for the electrons, right? So you can do a calculation, a semi-exact calculation. You can do numerics, whatever you want. This model has been studied to death, and you will find that the polons and bipolons are very heavy. Why is that? I mean, it's very easy to understand. If I make the coupling stronger, I'm making the potential well locally much deeper. The electron is localized. The hopping between different sites is becoming exponentially suppressed. So the electron has a harder time to tunnel. Harder time tunneling or lower effective hopping is equal to heavier quasi-particle. So that's why we get heavy polons and bicontinuity heavy bipolons. And that's why we get low TC. And actually this topic was quite debated in the 90s after the cuprates were discovered. There's a very famous paper about how bipolonic high temperature superconductivity is impossible. I actually encourage you to look at this paper even if you're in high energy, because it will be very entertaining for you to read, because Phil Anderson, I'm not sure what the high energy community thinks of Phil Anderson, but Phil Anderson is not on this paper, but he actually took a point about this topic, and there was a big debate and people yelling at each other, and it's published in PRL. So it's sort of funny in retrospect. Of course, it's not funny for the authors at the time, but it's funny and interesting in retrospect. And just to state the fact here, I'm not disagreeing with the conclusions of the paper. The conclusions of the paper is the cuprates are not bipolonic. So I'm not saying these results are wrong. What I'm going to say is this model is not the whole story. So basically everything I told you before is to a great extent because experimentalists in the field have believed so much in such a model that they assume everything that comes out of it is universal, even though I would say that they don't really appreciate universality in that sense. And so they assume that these are the generic properties of polons and bipolons. And we're going to refute this by showing that there are other sensible physical models that don't have these properties at all. Okay. So that actually gets me to the models, said models that I'm interested in. And I'm going to call them the hopping modulated models. And they actually have different names, and you might have heard of them. So one of those names is the Suschrieffer-Heger model, the SSH model, which is now widely known in the context of topological insulators. There's other names like the Pyros model. Why do we call it Pyros? Because Pyros is the guy who spoke about how phonons could modulate the hopping in a crystal. Regardless, it's very simple to understand what the model is, right? The model considers the situation where I have an electron, the blue circle here, hopping between sites, and the distance between sites are getting modulated, right? The ions are moving relative to each other. That's a very sensible thing. It happens in real crystals. And so you can linearize your coupling, and to leading order, this is what you're going to get. You're going to get a hopping from site I to site J, where I and J are neighbors, induced by a modulation of the distance between xi and xj, right? Between the displacement operator at site I and displacement operator at site j. And xi and xj are of course, operators. These are second quantized things, or first quantized in this notation, but you can second quantize. All right, so now you have this coupling. What goes on, right? So in 2018, when I was a student, I looked at this model. So this is what I'm calling Pyros in blue here. And I compared it to the Holstein model, this dogma model that I showed for a few slides, and it computed the mass of bipolons. So here on the y-axis, you see the mass of a bipolon measured in the units of 2 free electron masses. So when the coupling is 0, I have 1 because I have no bound state. So, and then I plot here lambda. Lambda is the dimensionless, the bare dimensionless electron-phonon coupling. And so let's look at the mass. In red, you have the standard density coupling model of the Holstein coupling. This is a log scale, so you see a straight line signifying exponential mass enhancement. This is correct. This is what we know about density coupling. But look at the blue line. The blue line, this model, the mass stays order 1 throughout. We actually still don't fully understand why that's so. We will understand a lot of different things about the model, but it stays order 1 throughout. So basically, we have a bipolar. I don't show you here, but strongly bound. The binding energy increases as we increase lambda, but the mass is basically very close to the mass of two free electrons. So that's very exciting, right? So this is in 2018. This is using an exact Green's function recursive approach. And that was exciting at the time, but of course, okay, so before I discuss this, maybe let me tell you why that could make sense. So you can do perturbation theory in the large omega limit. So this is not a physical limit. I'm going to go to the large phonon frequency limit. It's not physical because it's not, the phonons usually are coming from the ions, which are very heavy. So I'm going to pretend that the ions are very light. Okay? Happens in some exotic materials, but for the most part is not the case. And why am I going to do that? Because it's actually easy to do perturbation theory. So I'm actually going to do the perturbation theory for you on the screen. So imagine here, I'm going to take two electrons, the blue circles, one will spin up and one will spin down, and I'm going to do perturbation theory in this coupling. Okay, so what does this coupling tell me? This coupling tells me you can go from one side to another, either on the right or the left, by creating or annihilating a phonon on your arrival site or departure site. And you have to take care of the signs. That's what this coupling tells me. So let me do one of these processes. There are many of them, and we included all of them, but I want to show you one important process. So one of these processes allows this spin-down particle to hop to the right by creating a boson, this purple box, on its departure site. That's a legitimate process according to this Hamiltonian. Then we can go to the next order. And now notice that this coupling also means that the particle with spin up can absorb that boson and hop to its partner site. So I started from a configuration on one site, and they pair hopped into a neighboring site. So basically, they are forming a bound state by sharing the excitation and moving together. It's like two kids playing soccer. Instead of just standing and passing the ball, or football, passing the ball back and forth, they're running together. So they are in a bound state, but they don't have to sacrifice their kinetic energy. So basically, this phonon-mediated electron pair hopping is what we propose as an explanation based on this perturbation theory, and of course it's supported by the numerics I showed you here. And we were excited about this, but of course the normal thing happens. I go talk to people like experts in the field, and I tell them about this, and of course they don't believe it very much. And why is that? Well, there are two limitations. One, this is in one dimension, and if we want to talk about superconductivity is a two-dimensional and three-dimensional phenomena. And second, the calculation that I did, the numerical calculation, is in the limit when omega is on the order of the bandwidth. But if I want to do a realistic calculation, I need to go to omega much smaller than the bandwidth. Omega is the phonon frequency, so I need the ions to be very heavy, the phonon very small. So you have a question?
Yes, sir. So is this coupling supposed to replace the Holstein coupling or correct it? And then
in real life, or like in real materials, or in my picture?
In the modules.
No, right now I'm replacing it, but there are many papers now that examine when I have the two, and this physics survives.
So in principle, I expect both of them to be orders to be terms in
Yeah, so the Holstein model is not a term in expansion. I don't know anyone who knows how to write the Holstein model as a term in expansion. The Holstein model is written as a matter of fact. Okay? And people are convinced because when they do ab initio density functional theory, they just do things and they tell you, okay, it's an local electronic density modulation, and that it will look like. This is an expansion, but the other one is not. Okay? All right. Okay. So how am I doing on time? Okay. So so I'm getting to the exciting part now. So maybe I'll focus on this part, and then I'll flush the rest very quickly because I think that's the important part. So okay. So of course I'm excited about this, but if you look at the paper, you see the citations in the first couple of years, they're basically nothing because people were not very convinced. And then that propelled me to do more. Actually, one of the person who hired me to do a postdoc, Andy Millis, was kind of not super convinced about this, but he wanted to do more, and we did more, and we actually can go beyond these limits and verify what's going on. So now we study the problem in 2 dimensions. We're not going to study the same model, and the reason we're not going to study the same model is basically, as of today, we know no way to do this in 2 dimensions because of numerical limitations and same problems. So there's a cousin of the model that we thought about, in which you have hopping from site I to site J, but instead of having the difference between hopping between the phonon operators on I and J, you put the phonon on the bond. So this looks like a lattice gauge theory, except that there's no gauge constraint that's put by hand, and this is a phonon operator. And the reason we thought this is interesting, or there are multiple reasons for this. First is it has this character that the phonon is modulating the hopping. So we thought, okay, at least we will get a general understanding of that. And second, there are a bunch of materials that are actually almost well characterized by this coupling. So, and I know this community will maybe does not know about materials, but a lot of about the technical details of materials. But let me just give you a very fast idea. In the group race, there's discussions from a long time ago about bond buckling. So the bonds are buckled, and that basically is because of this coupling. In the pnictides, these are new types of superconductors that have been discovered recently. Here are measurements of that phonon mode, which corresponds to this pnictogen atom moving out of plane between the iron atom and plane, and when it moves out of plane, it actually modulates strongly the hopping between the iron atoms in plane. So that's in effect a bond, this motion modulating the hopping in plane, which is this cartoon. Okay? So we're not going to study these materials because these materials have a lot of other messy things. So this is a big problem in condensed matter, that models are very messy, the real life is very messy. We're going to study the simple model. So actually we started by looking at single polarons first, right? Because we didn't even know what happens. And we found that the polarons are light and they carry current. So that's very interesting. And there were but two groups that did this at the same time, me with a student at Columbia, and the UMass Amherst group, which is a very numerical group, which is an excellent as well numerical group, right? So we got the results at the same time. We put the papers on the archive, and we decided we are both interested in the bipolar problem, so why should we compete? We should instead collaborate. So, and we studied the bipolarons, and the major point here is this model is sign-free, whereas the other model that I studied in 2018 that involves the difference between xi and xj is sign non-free. So that other model, which remains very interesting, is very hard to solve. So we're going to solve this model with quantum Monte Carlo, right?
This xij, do you choose them, or is it part of your? Do you choose the parameter that you choose, the xij?
No, it's a harmonic. It's an operator. So I just I choose G. I choose. So I didn't write the full Hamiltonian. I have hopping of the electrons. I have a harmonic oscillator with
these are also operators.
Yeah. Everything is operators.
C is electron, X is a phonon.
Correct.
Okay, so this is a cubic type of coupling.
Yeah, exactly. So the other one's cubic type of coupling too, but the problem with the other one is that it involves xi minus xj, and in the type of Monte Carlo that we're going to do, you can't gauge away the minus sign, so you're stuck. Because we're basically going to do some type of Monte Carlo that is like a Feynman perturbation series. So here, you don't have that minus sign, so even if the Hamiltonian has a minus sign, you can send x to minus x, and everything is invariant, and you can deal with it, right?
Sorry, this also works for 3 dimensions or?
Yes. Yes. So I will talk about this later, but I will flash the result quickly because of time. Okay? So this is where we're going to solve, and we were ambitious. That not only did we solve the problem in 2 dimensions, we even put a repulsion, a local repulsion, which is called in the condensed matter community a Hubbard-U repulsion. This is a repulsion between up and down on the same site. Okay. So what's the strategy that we're going to do here? We're going to solve the 2 electron problem only. So we have 2 electrons in a crystal. I forgot the systems that we studied, but they're humongously big. I think they're much bigger than 100 by 100 with quantum Monte Carlo. We're going to compute the binding energy, and we're going to compute Tc, which is what we care about most, using the following idea. So in 2 dimensions, if we have bosons, which will be the electron pairs, they form a superconductor below a temperature Tc that belongs to the Brzezinski-Kosterlitz-Thouless universality class, and Tc is given by some number times the density of the pairs, which is the bipolarons, over their mass. So what we're going to do is we're going to compute their mass and plug into this form. This is log-log corrected, but we're going to work at the limit where the log-log correction is small. So basically, you're going to approximate this by the density over the mass. The density is a free parameter because we can just change the density of pairs, and we just need to compute the mass. That's what we're going to compute from Monte Carlo. And this number is a universal number, order 1, but it's been computed by numericists to very high accuracy, and it turns out to be 1.84. Okay, so that's the strategy. And of course, we're interested in the maximum TC that we can get from this mechanism. So naively, I could just crank up the density and maximize TC, but that will be very stupid, because if I do this, well, at some point, I will have a dense system. This theory is not correct in the dense limit. The bipolons will start to overlap, and I can no longer talk about superconductivity. So what we were going to do is the following. We're going to find the maximum TC by assuming that at the largest density for which this state would be stable would be the density when these bipolons, which are in 2D, are disks that are touching. So that means the density, the maximum density or the optimal density, is 1 over the radius, pi r squared, of the 1 over pi r squared of the bipolons. So I can just replace the density here by this, and this is the formula I'm going to get. And now that means I can compute the mass and the radius of my bipolaron from quantum Monte Carlo and plug in here. So the curves I'm going to show you basically mean that for every lambda, for every electron-phonon coupling, I am optimizing, I'm not working at the same density, I'm optimizing the density such that I compute the mass and the radius of the quasi-particle to find the maximum possible TC. Okay? So this is what we do. This is a quantum Monte Carlo approach. I don't have time to discuss, but it's actually a diagrammatic approach. It sums all diagrams numerically, right? This is invented by Prokofiev and Zvistinov. I'm happy to talk about the technical details, but for the sake of time, let me just get to the main results. So here's the main result. On the y-axis, I have TC in units of the phonon frequency, omega. On the x-axis, I have lambda, the dimensionless electron-phonon coupling. And I have a lot of figures here, a lot of curves here. Let me focus on the following. So in blue, I'm contrasting the new model, the hopping modulated model that I studied. In orange, I have the Holstein model, this old dogma density coupling model. And I have 2 types of theories. I have the bipolaron theory, which is the theory that I just described to you in the solid lines. And then the open symbols are Migdal-Eliashberg. So let's look at the Migdal-Eliashberg. I have 2 types of Migdal-Eliashberg. I have this orange bond model, the hopping modulated model, and then the blue density coupling model. Both are below this empirical bound of 1/10 of omega, right? So there's no surprise. Migdal-Eliashberg, this one loop calculation really does not get you better than 30 Kelvin. I'm just putting some value of omega here that's realistic, and as a guide to your eye, I'm showing you where 30 Kelvin sits. Okay? So you can forget about the Migdal-Eliashberg lines now and focus on the bipolaron theory. So the bipolaron theory, the first line we should focus on is this Migdal-Eliashberg-Holstein, this solid line. So this is finding TC from condensation of bipolarons in the density coupling model. Indeed, it's very bad. It's below the bound. Now let's look at the blue curves. These are the new results. So these are large-scale simulations in essentially all parts of parameter space. We're going from omega on the order of the hopping all the way down to omega on the order of 1/10 of the hopping. Okay? So all these different curves. And you see that all these different curves are above this empirical bound. So indeed we have what I call bipolaronic high temperature superconductivity. This hopping modulated coupling, this bond coupling, is producing in a large swath of parameter space for even a repulsion that's very large, U equal 8T, curves that are distinct from all other theories that produce high TC from the formation of pairs, right? Again, I emphasize that on the x-axis here, for every lambda, I am actually computing a different density. So the density at this lambda is different from the density at this lambda. I'm optimizing the TC. This is the maximum possible theoretical TC that I will get from the condensation of bipolars in 2 dimensions. Okay, so now I think I probably have 10 minutes or 5 minutes. Okay, so I think I can flash what's next here. I don't have to go into the details. So people, when we showed this to people, of course, more and more believers now, but there's still some doubt, which is, what about the Coulomb repulsion? And someone asked, how about 3 dimensions? So this is what we did here. Now we do the full Coulomb repulsion. This is an on-site U. We're on the crystal. We're on the lattice. So we're an on-site U and the long-range part, and we parameterize it in the following way. We said if U is 80, that's quite a big number. That's the number in the transition metal oxides, the cuprates. The long-range part, as in typical oxides, will be U over 10, and then you go as 1 over R. Okay? So that's what we do here. And we're in 3 dimensions now. And we're going to repeat the same story, except now, instead of the density, Tc is the density over the mass, it's the density to the 2/3 over the mass, right? And then we know these numbers from numericis, so I don't want to go into the details. We repeat the same thing, but here's the results. Okay? So you put Coulomb repulsion. Before we did this, we thought, okay, Coulomb repulsion will destroy everything, because what we're relying on is that the bound states form and that they still can hop. And when you put a repulsive U, if this bound state has finite size, it avoids the local repulsion. That's why they can move. But if I put a long-range U, where are they going to avoid the repulsion? Basically, it becomes very bad, because if you have a repulsive U, you need to increase the coupling to compensate for the repulsion, which will make them heavier. Turns out not to be quite the case, right? So here you see the results. Again, the density coupling, the orange line, is terrible, right? Tc is basically 0. These curly lines mean we actually have no bound state here. However, the blue line, when omega, when the phonon frequency is large, we have reasonable values of Tc. And when omega is small, it's small, but it's not bad. It's still higher than in some region than the upper bound, right? So here's my salient features. We think we have a generally robust mechanism. I don't think I can call it universal, because I don't have a field theory that I can make it universal, but if you have an idea, please go for it. We have a general theory that produces small in size, yet light in mass bipolars, and that leads to relatively high Tc. There are other salient features here that I didn't highlight. There's non-monotonic dependence of this maximum Tc on the local repulsion. So basically, increasing U increases the maximum Tc before it decreases. So this is an important feature for people who are interested in superconductivity, for context in the cuprates. The long-range repulsion reduces Tc, so screening would help. Yet even if the long-range repulsion reduces Tc, still Tc is roughly higher than the upper bound that we have from all theories.
First of all, the screening is dependent on which energy or which.
By screening here, I mean screening from some other mechanism. So, for example, in 2D, I can screen by gates.
You screen by?
But gates. If you have a two-dimensional material, you have to gate it, right? So that screens. So screening is useful in that sense, right?
You have screening because of the existence of other electrons, right?
Yeah, no. So that's not what I meant by screening here. Like, screening for me is an input parameter. Okay. So keep screening because of an emergent thing that will be very interesting, but we have not done that. Okay?
I mean, there's a consistent way of calculating the long-range repulsion, right? I mean,
Yeah, but that's not what you did. So here.
So you put there.
Yes. Exactly. Right. So. Okay. So now, before I conclude, I think this is one slide that will resonate a lot with the high energy theorists. So, okay, I have this effective story that I told you about in the large phonon limit, large phonon energy limit. I can do perturbation theory, right? And I get virtual processes. But it's far away from the realistic limit. The realistic limit is the opposite limit. When omega over t, the phonon frequency compared to the hopping is much smaller than 1. I don't know how to do perturbation theory in that limit, or I didn't know for a long time. Now I know, right? And the results, the numerical results, show that the physics works in that limit. So that's encouraging, but why? So here's a brilliant idea that we came up with 2 students at Stanford when I was a postdoc there, and this is what we did. So basically, I'm going to pictorially explain it, and I'm happy to talk about the details offline. You can first set omega to 0. If you set omega to 0, these X operators, these phonon operators, become classical, because they become conserved quantities. So now I have a problem in which I have electrons coupled to classical configurations. Okay? Now, That's good news, because electrons, bilinears, coupled to classical things, we know how to solve it. Just do gradient descent and find the minimum. So that's what we do here on the left. And that's what we find in these models. We find that the bipolar is this star configuration. So that's already interesting, because people always assume that the bipolar is going to sit on one side. Actually has the wave function has support on a star or a cross. Okay, good. So as of this is not very valuable. What is valuable now is you want to put quantum corrections. So how do you put quantum corrections? You do an instant tone calculation between different classical solutions, right? And so here we compute the instant tone tunneling barrier against the inverse of the coupling. So when the coupling is infinite, this is 0, and when the coupling is 0, I'm going to the right-hand side. So let me go from small coupling, which is all the way here, to large coupling. I go from small coupling to large coupling, the instant tone barrier grows. In standard theories, in electron form coupling or in double barrier well or whatever, the instant tone barrier will keep growing, and then at infinite coupling it will diverge, because you're just making the coupling stronger. So the distance between the barriers is becoming very high. It's hard to tunnel from one barrier to the other. However, actually something is crazy is happening here. The barrier flips and goes to 0. It's not approximately 0, it's exactly 0. So there's no tunneling barrier at infinite coupling. So why is that? We analyze this, actually, it's because there's a family of degenerate solutions. So this solution is not only unique, there's a family of degenerate solutions that are connected by smooth deformations in this limit. So basically in this limit, you can deform this bond here, and this bond here, and those 5 bonds, and slowly deform that state to a different state that's at a different site, because they're degenerate. So there's no barrier for tunneling. And then you perturbatively go away from the infinite coupling limit, you still see remnants of this effect. You lift the degeneracy, but the tunneling barrier is not super huge, so you have a light mass. So basically, we have here a strong coupling theory for why this is the case. And then from this strong coupling theory, we can derive asymptotics about TC. So that's what we did here. For the Holstein model, TC is exponentially small, as we already knew, density coupling, because the mass is exponentially large. So, remember to remind you, TC is n over the mass. If the mass is exponential in lambda, I can just put this as an exponential here.
Is this weak strong coupling type of thing?
No, both are strong coupling. Both are strong coupling from instant tones. Okay? However, the bond phonon modulated hopping, this model that I'm showing you the results for here that have this anomalous behavior at infinite coupling, has a TC that's n over a mass, and then I can take the mass, which is exponential, and put it in the numerator, and it will look like this. That is stretched exponential. There's a square root of lambda that appears here. So that's why TC is significantly larger. It's exponentially larger than the conventional models. It's still exponentially small, but it's a stretched exponential.
What is the number here?
The electron phonon coupling, the dimensionless electron phonon coupling. Yes.
So if you look at the usual you have orthogonality catastrophe, right? Between the two, the hopping, and the two sides are orthogonal if you take into account the electrons, right?
Yes.
But here, this is not the case.
Correct. Because there overlap between the two sides. This site and that site already, the wave function has support on both. So you can't have this Frank-Condon suppression. That what I think you're saying is basically a type of orthogonality catastrophe, because overlaps here are so you don't have that. That's precisely that. So that's why for a while we were struggling. How do we do the strong coupling version of this? Then we came up with this idea from instant tones, and we did it, and we found this. It was very satisfying that we find that it's still exponentially small, which makes you, if this was like growing exponentially, for example, or growing even linearly, it will be crazy, right? It will not be a physical thing. But it is a stretched exponential, so it's still much bigger than Holstein. And in real life, you don't go to lambda in the exponential scale. You go to lambda order 1. So lambda order 1 will already give you sufficient enhancement.
So these are different models?
Correct.
So you have the polar on one case where you get the orthogonality catastrophe, and then you have the bond modulation where you kill it, right?
Yes,
So there is
yes, but
competition
I
between the
I
two.
wouldn't say the polar. I would say I have the Holstein model,
Yeah.
where I have the orthogonality catastrophe. I mean, I wouldn't call it orthogonality catastrophe.
The classical limit,
Yes,
right,
exactly.
yeah.
But then and then I have the hopping modulation, where I basically kill it, and I give rise to other interesting phenomena. One of which we're very excited about, is this enhancement of DC. Okay, so I'm done. I just want to thank you for your time, and happy to take your questions.
Thank you for the nice talk.
Thanks for the talk. Quick question. How all this is changed in 3 dimensions?
Yeah, so we didn't do this instant calculation in 3 dimensions. My student's trying to do it right now. It's hard, so let's see. But we did this numerical calculation in 3 dimensions.
Okay.
Right? So I don't think it's very sensitive to dimensionality.
Okay.
Well,
Yes, one basic question. The electron density, how do you regulate that? How do you control that? Or is it depends on material?
yeah, so this is actually the main loophole in our theory, right? So the way I take care of the electron density here is really not well controlled. I am starting from the zero density limit, and then I say I know the properties of bipolar ions very well. Now I'm going to crank up the density, and when I go away from the zero density limit, these bipolar ions repel each other. That I know because I did other calculations I didn't talk about here, so we're not worried about this. And then there's no phase separation or anything like this. And then these bipolar ions are isolated. That's fine. And then I say, well, I'm going to go to the density that maximizes DC, and I assume that this density is when these bipolar ions are touching, right? So that's where things may not work. We don't know, right? I think it's probably okay, but we don't know. The way to go beyond this, which we're trying right now, is actually to do a numerical or an analytical approach that includes the density, as a matter of fact. Right now, we took the bipolar ion limit, right? It's sort of a different philosophy. Instead of taking Fermi liquid and doing Micheli-Algebra, taking the bipolar ion limit and building a many-body state from bipolar. Does that answer your question?
Yes. And I have a second one. These bipolar, remind me a lot of mesons in QCD. The strongly coupled theory, somewhere you expect massive things, and then somehow there's an underlying global symmetry that gets broken in this strong coupling unit, and then you get quasi-Goldstone worlds at the end of the day. Is there something?
There is something.
Here or some speculation about something similar?
I can speculate. So I don't know QCD very well, so I can't answer that. I don't know what will be the Goldstone mode here. What I can say is there are.
These are supposed to hold from one side to the other. Is there some kind of breaking of translation invariance or something?
It's not built in the like I have to build it in the theory. So it's not. It's okay. It's not apparent to me. But what I can say. So we should talk more. But what I can say is there are similar theories in the context of the TJ models of the cuprates by Fabian Grust and others. They're similar. They're not exactly the same, but the idea here is that now instead of having bosons, you have phonons, you have magnons, and then there is a mapping to mesons, and so there might be some of that here too, but I really haven't flushed it out.
Without there's some symmetry.
Isn't it phonon?
But the phonon is gapped. It's not an acoustic phonon. So I don't. So I don't know how to. Maybe versions of the model that are acoustic. We're doing some stuff in my group right now with acoustic phonon. We should talk more. I'm really speculating at this point. I don't know.
So you get this phone hopping modulated in one dimension too, or?
I can.
And then how do you compare it with the different
Yeah, qualitatively similar, quantitatively not the same. There are some differences. Quantitatively, like their differences are not like exponential differences. They're all one, right? So, but qualitatively similar. But there are differences. So it's really not universal. That's what I mean. I don't know how to formulate anything universal. They're all microscopic models. They seem to have similar behavior, but I don't have a sharp way. Like the previous talk, I'll say that they're observationally similar, but I don't really know how to make them connected in a universal sense. but there might be a way, right? Like I tried to think about like, what if I take a continuum limit? How can I write the kinetic energy coupling? I'm sure folks have done that, but I haven't gone deeper yet.
Last question.
Do you see it effective to go with your systems for smaller ultra-constrained cases?
We tried a long time ago when I was working with CREMS. The major issue that I don't know how to resolve yet is I need two spins on the same side. So I know how to make with ultra-cold gases things that are, this is an object that couples to phonons on this side, and this is another object, and they talk to each other. But if I want them to have a spin degree of freedom, a spin favor, which is really what would be nice for superconductivity, I want these two quasi-particles, which will become my two electrons or two electronic states, to be on the same side. I don't know how yet to do this. I thought about this a while ago with cavities, but I didn't push further, so I'm happy to talk more.
Since Yanis is the organizer.
Okay.
So does this explain, like, the linear resistivity of the two plates?
Okay, no, so first of all, I want to warn that I have not really touched that topic with these models at all. The cuprates are, in my personal opinion, which is you should not take as an expert opinion, is very messy because correlations and phonons are probably important there. Some people think it's only correlations, some other people think it's phonons. I think the more recent view is the two are important. So I don't think that this would explain it. What I can say, there are some calculations by Wilson and Berg and collaborators where they show that these models really give, or variants of these models in large N, give linear T resistivity and saturation and so on. So there is some hope, but there's need for more work.
But this is a BCS.
Yes, I'm right now doing just superconductivity. I didn't do any above TC. I didn't do anything, but Kevelson did, but did with large N.
With bipolar?
No, so without bipolar. Just take finite density electrons. He did bipolars for other things, but finite density electrons coupled to phonons. Now promote the phonons to large N. So they're N flavors of phonons, right? I forgot the details. Actually, I think they're N flavors of electrons coupled to N squared flavors of phonons that allows you to do 1 over N expansion, and then you can get linear and T resistivity for some class of models. It's very interesting, but of course we would like, and I think he would like to do it in more, not large N. We have not, and we don't know. So.
Thank you very much.
Thank you.
Okay, shall we get started? So this is the second part of the first day of the workshop, and I'm very happy to introduce Professor Spyros Sokriadis, who started here in Athens, then went to Cambridge. He did his PhD in Oxford with John Cardy, and then, well, he worked also with Calabrese in Trieste, I think, before moving back to Greece and going to Crete. So he's going to talk to us about Hamiltonian truncation tensor networks. Thank you very much.
Thank you for the introduction, and thank you for the invitation to this nice conference. Okay, so today I'm going to talk about a work in progress that we are doing in collaboration with the group of quantum information theory in Berlin, Free University of Berlin. And it's about a new numerical method for the simulation of 1+1 dimensional quantum field theories, which we call Hamiltonian truncation tensor networks. Here is an outline of my talk. I will be pedagogic a bit. I will introduce the problem of quantum many-body physics and dynamics, and the problem of the simulation of these models in classical computers. And then I'm going to introduce our method, which is based on a combination of two earlier methods, one called Hamiltonian truncation, the other tensor networks. And then I'm going to show results for two models that we studied, the Sine-Gordon model and the Massey-Schwinger model. Okay, so the central problem in quantum many-body physics, and more specifically dynamics, is the problem of quantum ergodicity. We are interested in the problem of how do quantum systems involving a lot of interacting, a large number of interacting particles or degrees of freedom tend to equilibrium. I start from a state that is out of equilibrium, and I want to see how such systems tend to equilibrium, if at all. This problem is, of course, a central problem in statistical physics, which has puzzled researchers since the pioneers of statistical physics and quantum statistical physics in particular. And it has, to a large extent, we have understood what happens in the classical case, but in the quantum case, it's still unclear. There are still open questions as to how a quantum many-body system loses practically information, scrambles, and in the end we get something that looks thermal at large times. And of course, as I said, this is a long-standing problem, but it has seen renewed interest recently due to experimental advances. So we can do quantum simulation experiments in tabletop experiments. And on the other hand, if we are asking about, if we put this problem in the context of quantum field theory, we can see that it's a very central problem in a lot of open problems in theoretical physics, theoretical high-energy physics, the black hole information paradox problem, the dynamics of the early universe, but also problems related to heavy ion collisions and the physics of quark, gluon, plasma. So it would be very important for these problems to get an understanding of the mechanism of equilibration in a quantum many-body, in a quantum field theory. Okay, so but let's first try to understand why it's difficult to simulate, to study quantum many-body dynamics. Well, the problem is the so-called curse of dimensionality problem. Let's consider a system, the simplest the simplest quantum many-body system that we can think of, a chain of spins, two-level degrees of freedom. We know that to describe the quantum state of such a system, assuming that it's in a pure state, we need to specify the vector, a vector in the Hilbert space, whose dimension grows exponentially with the number of qubits. Each qubit has two possible states, 0, 1, up or down. And then if I have n such qubits, then obviously I have 2 to the n dimensional Hilbert space, which means that not only the state, the vector in the Hilbert space requires a lot of memory to store it, but also the Hamiltonian, all operators that act between vectors in such Hilbert spaces increase also exponentially fast with the system size. And in the end, the cost of calculating the ground state or calculating the time evolution in such a system is very high, meaning the complexity of the problem is exponentially large, exactly because the dimensionality of the Hilbert space increases exponentially with the number of degrees of freedom.
Does the Hamiltonian commute with the angular momentum, with the total speed?
Well, I'm considering here a general system where I'm not specifying the Hamiltonian.
It's much easier, right?
Not much. So we can gain some speed up with exploiting symmetries, but not much more. I mean, there are methods where in the large n limit you can do analytical tricks. But if I want to get the exact answer for any finite n, large finite n system, then I would have to deal with this problem of calculating the action of a huge object, the Hamiltonian, in a random vector in the Hilbert space, in an arbitrary. Let's discuss this. Okay, so this problem was noticed very early in the development of quantum theory, already Dirac, in a talk in the Royal Society, mentioned that we now have everything. We know all the equations describing quantum mechanics, and the problem now is that the equations are too complicated to be solvable. So we need to find approximate practical methods to get the answer, the physically relevant answer of what is the dynamics or the physics in general of such many-body systems. And that gave birth to the idea of classical simulation. We need to find ways so that the classical computer can simulate approximately a quantum many-body system. On the other hand, another approach is, of course, quantum simulation and quantum computing. So as we all know, the idea here is to use a quantum system to simulate a quantum model in such a way that we go to the lab, we do measurements, and we get answers to questions like solving the strongly correlated models that were described in the talk, in the previous talk. And a universal a machine that can do calculation, can simulate any quantum problem is called a quantum computer, but which are still under development and progress is being made. But on the other hand, we also have quantum simulation platforms using cold atoms that can simulate specific models, designed exactly to simulate specific models, and here progress is already impressive. So we can use cold atoms to simulate quantum field theories like those that I'm going to describe in a while. I'm not going to talk about these, but it's something interesting to discuss in another talk. Okay, but the main breakthrough in the former direction of classical simulation was made with the introduction, with the discovery of tensor networks, which come under different names. In mathematics, in the mathematics literature, they are called tensor train. It's called tensor train decomposition. In the physics literature, it's the matrix product states. And they all belong to the umbrella term of tensor networks, which have different, by now, different techniques and different geometries and topologies have been used to exploit this idea in different contexts. Let me go now to see these methods in more detail. So our main objective is to simulate a quantum field theory, which of course is a quantum many-body system, but with the detail, well, the important distinction from other models that they are continuous. They are continuous and relativistically invariant models. And our goal is to do such tasks as finding the ground state or thermal equilibrium states, or to calculate out of equilibrium dynamics. I start from some specific initial state and I evolve it under some Hamiltonian described by some quantum theory model, and I want to see the behavior of the system at large times, which is relevant for problems, for example, in quantum cosmology, the forced vacuum decay, and so on. Now, as we already said, we have the curse of dimensionality problem, which means that since in any quantum field theory I have a lot of degrees of freedom, seen either in real space or in momentum space, when I increase the number of degrees of freedom, I will have the curse of dimensionality problem. I will have an exponential blow up of the dimensionality of the Hilbert space, where I have to solve, to simulate my problem. For that, we'll use tensor networks. This is the standard solution. On the other hand, there is the additional problem that because these models are continuous, if I see them in real space, the degrees of freedom are not just many as before, but they are infinite. They are continuous. So I have to find, I must do some truncation before I am even able to write the problem as a big matrix that I'm going to deal with tensor networks. So we have to find an efficient way, a good way, by guessing or using some analytical understanding of how to truncate the space in the first place, how to truncate the degrees of freedom, how to choose them conveniently so that we can do the simulation. And here we need to use, we use the idea of Hamiltonian truncation, which is based on renormalization group theory, and it's based on the idea of expanding the Hamiltonian as a perturbation, not necessarily weak perturbation, of an exactly solvable model, so that we can represent it as a finite matrix representation, approximation. Okay, so the combination of these two ideas, Hamiltonian truncation and tensor networks, gave birth to our model. So let's go and see first the Hamiltonian truncation method, and then talk about tensor networks. Okay, so in Hamiltonian truncation, the problem is that we want to find the spectrum of a quantum field theory, and to have a finite dimensional representation of the system so that we can do numerics, we place the system in finite volume, so the energy levels are discrete. And in addition to that, we will have to apply a maximum, some cutoff, so that we don't have infinite energy levels, right? So we do that by expanding the Hamiltonian in the basis of some exactly solvable model. Say I have an interacting model, I split it to the free part plus some interaction, and I expand the interaction, delta H, in the Fock basis of the free part, right, where the free part is just diagonal. So as long as I can calculate the matrix elements of the interaction of delta H in the basis of H naught, of the free part, the easy part, I can represent the Hamiltonian fully as it's an operator. I can calculate one by one the matrix elements, and if I find some way to truncate the Hilbert space, the Fock space of the free part, then I have a finite matrix approximation which I can diagonalize numerically, and then increasing the cutoff, check if convergence of the spectrum is achieved. That's the idea. Now the non-trivial part is how to do this truncation. So one idea is to apply a high energy cutoff in the Fock space of the free part. More generally, if I want to have a justification of what's the optimal truncation, then we should choose the the exactly solvable part as the conformal field theory that describes the ultraviolet limit of the theory, because then we know that the perturbation affects the low energy part of the spectrum, but at high energies it becomes weaker and weaker. So by increasing the cutoff, I'm going to get smaller and smaller corrections, which in the end guarantees that my spectrum will converge as I increase the cutoff. So there is some non-trivial idea here that if I want to get convergent spectra, I should do the splitting into the free and the interaction part in the basis where the free part is the CFT of describing the UV limit. I could write a model in different ways, which are all equivalent, right? And then I could see naively that, okay, there is a free part in fermionic basis. I treat the interaction in terms of the fermions, and I move on. But then if that perturbation is not relevant in the RG sense, then the convergence of the spectrum is not guaranteed when I increase the cutoff. Yes.
But this way, there is a UV fixed point, or the theory has a completion, a UV completion, or the full general?
That's not fully general. We have to restrict ourselves to models that have a UV limit. And
but it has to be composed, that limit,
well, yes, I mean, we are using RG theory and standard. We have to rely, I mean, if we had a marginal operator, for example, a marginal perturbation, that method wouldn't work. So we have to make sure that in the UV, it's in models like that are asymptotically free in this general sense, not necessarily in the Gates theory sense. In models where the interaction becomes weaker as we go to higher and higher momentum modes, so that we can treat them perturbatively, that will hold. This property should hold.
Excuse me, just a very quick question. I assume that you are losing the completeness and also the unitarity by this truncation, right?
No.
Very
Why?
Because
I mean, well, unitarity in general, if we talk about Hag theorem, right, there is no way to connect.
If you have a completed basis and you truncate this basis, the completeness is not exact anymore, right?
True, of course, we apply some truncation.
Therefore, you are losing what maybe unitarity.
Unitarity, we are losing, as I said, even mathematically speaking, there is no unitary transformation that can take me from an interacting theory.
Unitarity in the sense of completeness, this way. But the sum of all these states is normalized to one.
I don't know if that makes it different. But certainly, we are approximating the theory, so we are breaking. I would even worry more about relativistic invariance, for example, and we have problems with that. The theory is no longer relativistically invariant, which is something that we would wish to preserve. So all of these are problems, of course. But the question is if by increasing the cutoff, I recover the theory that I want, the physical information that I want. So we expect that low energy properties like the ground state energy, the energy gap between the ground state and the first excited state, are convergent quantities, but we cannot be sure about other aspects. Yes?
What is the CFT in the IR? So can you have a truncation around the CFT?
Yes, okay, so that's also, yeah, so then the spectrum keeps changing every time we change the cutoff. So I didn't say that the cutoff is high energy cutoff in the CFT, right? Right. So if I change the cutoff now, then the spectrum keeps changing, but we know how it changes. So there are works where irrelevant operators are used, and then again by matching with the scaling that we expect from RG theory, we can extract some non-trivial information about such interacting models, such perturbed models.
Just to clarify, when you say irrelevant, you mean around the H0, right?
Yes,
not
exactly.
Around the full interacting system.
No, around H0. Okay, so to have a concrete example, let's take this Hamiltonian, which describes the sign. It's the Hamiltonian of the sine-Gordon model. So it's a massless free boson Hamiltonian perturbed by a cosine interaction. And the splitting is exactly this. So the free part is this, H0, and delta H is the interaction. And this is a relevant interaction for delta smaller than for some parameter regime. And then that guarantees that the low energy spectrum is modified. So the original model is critical, so it has no energy gap in the thermodynamic limit. But once we switch on the interaction, we get an energy gap, while the high energy part of the spectrum doesn't change that much. Well, it changes in a weaker way than the low energy part, in a perturbative way. But still, we have, as we said, the Hamiltonian truncation, we have the problem of curves of dimensionality. So when we increase the cutoff, the matrix that we get, okay, this is because it's a PDF. It was supposed to be an animation. Anyhow, so we increase the cutoff and we take larger and larger chunks of this matrix representing the Hamiltonian, and we soon realize that the number of states in the basis increases very, very quickly. It doesn't increase exponentially, it increases like the exponential of the square root of the truncation cutoff, the partition number basically. But still, it increases so fast that we have severe limitations on what parameter regime of the model we can explore in this way. Okay, so here is why we need to invoke the power of tensor networks, and I'm going to introduce this concept now. So tensor networks are representations, offer a representation of a quantum n-body state and of operators as tensors of contracted small size tensors. So let's see this idea in more detail. the wave function of a quantum many-body system can be expressed in the basis of the Hilbert space as a tensor with indices as many as the degrees of freedom, and where each index takes as many values as the possible values of these quantum degrees of freedom. So in the example of qubits that I mentioned earlier, spin 1/2 degrees of freedom, I have two possible values for each spin, and that gives me the amplitudes of the state represented in the Hilbert space, gives me the tensor that fully specifies the quantum state. So these amplitudes C, N1, and N are the tensors I'm talking about. And this is a huge object, as we said earlier, and now the idea is to represent this approximately as a network of tensors which are contracted with each other and which have a smaller size. So for each of the physical degrees of freedom, physical indices, we have one small size tensor contracted with some auxiliary index with its neighbors along this chain, or in other words, tensor train as it's called, in such a way that the original tensor is approximated by this network. And you can check that the memory size, the memory cost of this representation is much smaller. Of course, it's not exactly the same tensor. It's an approximation of that. But as we will see, it's an approximation that works well under some very, very clear physical conditions. So we can see how one can, if you give me such a high dimensionality tensor, I can represent it as a tensor train by doing the singular value decomposition that we know from linear algebra and truncating the smallest singular values. I don't want to go into many details here, but very quickly, if I have a matrix that I represent in this Penrose notation, I can write it, I can break it down to USV doing a singular value decomposition, and the S matrix here is a diagonal matrix. And now if I want to approximate this matrix, I can just throw away the smallest singular values as long as they are small enough under some error threshold condition. And then I can multiply them again and get an approximate version of the original matrix. But instead of contracting them, I can keep them in this form and represent the original matrix as the contraction, the multiplication of two matrices, which in the end will have a lower dimension, because instead of an n by n matrix, I have a matrix with dimensions n times d plus d times n, where d is the so-called bond dimension that controls the accuracy of the approximation. So if I keep the d largest eigenvalues, the size of the smallest one, those that I threw away, will give me the error that I'm making in this approximation. And I can do that recursively, one by one, between all physical indices in a tensor with many indices. And this way I can get the tensor train representation that I talked about earlier. So that's the way of taking an approximate tensor network out of the original tensor, but we actually want to avoid writing the full tensor in the first place. So we want to forget about the original tensor and represent both the quantum states and the operators directly in terms of these tensor networks, and then do all the linear algebra tasks that we need to do in order to calculate ground states and equilibrium and time evolution dynamics in terms of these objects. Yes?
So the idea of this thing is basically you're putting all the degrees of freedom in bonds, which effectively are hops, right? It's kind of like particle-hole excitations that you keep from the E to the N. You go only to the
you look at hops between two neighboring sites, if you want, right?
They don't really have a physical meaning. They are these auxiliary indices encode all the correlations from one side of the system to the other. And as we will see in the next slide, if I make a cut of the system, if I partition in two parts, then the size of the necessary bond dimension that I need in order to accurately describe such a state is related to the entanglement, to the amount of entanglement between the two parts. So if I have low entanglement states, then I can represent them accurately with such tensor networks. If instead I have high entanglement, volume low, right, then I can't represent them in this format. If I have area low entanglement, if I have a state where the entanglement between any cut of the system does not increase.
But this is this is exactly the point, that you have local interactions in the
Exactly.
system, and that's where the hop kind of issue comes in, right?
Yes, that's right. So then the physical reason, so the criterion is whether I have low entanglement or not. Now, the physical condition for having low entanglement, or we can't obviously find all ways of having low entanglement, but states that are ground states or low energy states, eigenstates of Hamiltonians that are local and they have an energy gap, they satisfy this condition. So they have area low entanglement, meaning that if I split the system in two and change the size of the splitting, then the entanglement stops increasing at some point if I have a linear chain. If I am in higher dimensions, area low means that the entanglement between a subsystem and its complement increases with the surface, or the interface surface between the two parts. But in one dimension, that means, exactly because there are only two interface points, this means that it doesn't increase with the subsystem size. So if there is a maximum bound on the entanglement, then I know that the bond dimension that I need in order to describe such a state is finite. It doesn't increase when I take the thermodynamic limit. And that's why these methods, the tensor networks, work well for one-dimensional systems, states that correspond to ground states of local Hamiltonians, and that have an energy gap between the ground state and the first excited state, so that we know that correlations decay exponentially between different points. Yes.
What about topologically ordered phases? It seems to be losing those as well, right? Because they have long range entanglement.
Yeah, that's another story. So it requires special treatment in this case. So
it can be done, or it can't?
It can be done. So, but in different ways. Okay. So I'm talking here about splitting the degrees of freedom in real space. So for topological, you have to do something more careful. Okay. Now okay. So as I said, the entanglement is the criterion, the crucial criterion of whether these methods would work or not. There are different versions of this method for two-dimensional systems or models at criticality, gapless models. There are even versions that work well for quantum chemistry applications. So I have a molecule and I want to solve the Schrödinger equation. Now we have ways to do that more accurately, at least for some simple molecules. And in general, I can't state how important these methods have been for condensed matter physics. So we have plenty of discoveries that wouldn't be possible otherwise in the last decades, and which guide our physical insights. So we can do now numerical experiments, and we do not have to rely on effective descriptions which are uncontrollable approximations. Like in the past, we had to use field theory. Now you don't have to use field theory to study lattice models or condensed matter. Okay, now let's see how we can merge these ideas in the for our purposes. So the models I'm interested in are the Sine-Gordon model I mentioned earlier, which is equivalent to the massive steering model, so a model of interacting fermions in one dimension, but also the 1 plus 1 dimensional version of QED, which is called the massive Schwinger model. Okay, so using the bosonization mapping, a mapping between fermions and bosons that you know very well, it's in duality, in 1 plus 1 dimension, I can map this model to a bosonic theory, where I have a free massive model now, perturbed by an interaction still of the cosine form as for the Sine-Gordon model. But now the free part is a massive theory. Okay, so I'm focusing on these two models, and the setup of the method is the following. So I discretize the system not in real space, but in momentum space. I can do it in real space, and then we have lattice field theory, right? And these methods I was talking about have been applied to lattice field theory quite successfully, actually. We'll see some examples. But we do it in momentum space exactly because the momentum space allows us to use the Hamiltonian truncation approach that I mentioned earlier. Okay, so in momentum space, for these two models, what I have is system of bosons, so harmonic oscillators originally for the free part, perturbed by an interaction, which now couples all the momentum modes together. So this gives me long-range couplings from all momentum modes to all other momentum modes. So I represent my quantum states and operators as chains of such tensors. And in order to find the ground state or do time evolution for such models, I will have to first construct the Hamiltonian in this format. So I have to construct the Hamiltonian in the so-called matrix product operator, MPO form. Okay, in practice this is done as follows. The free part is just a sum of independent harmonic modes, which can be easily represented in this form. The interacting part is constructed out of exponential operators, which can also be expressed as matrices that act on each of these momentum modes separately. So you can write exact formulas for the matrix elements of these operators between any Fock state to any other. But the problems arise when we construct the integral overall space of such cosine interactions, because at that moment we have to restrict to apply the momentum conservation condition, which comes naturally when I integrate a local operator, right? And that means that the het and the bra states, the in and the out states of my Fock space must have the same momentum, total momentum, in order to construct a Hamiltonian. Now this is represented by this Kronecker delta that matches the in-out momenta of all the modes, which in tensor network graphical representation means that we have a huge tensor with as many indices as the momentum modes, contracted with all the individual tensors representing all the other pieces of the Hamiltonian, the interaction basically. And now this is very challenging because I still have the curse of dimensionality. If I had this form, then I wouldn't be able to do anything beyond that point. But we managed to find a way to break this tensor down into smaller tensors, so as a tensor train in tensor train form, by exploiting some quantum number preserving tensors, as they are called, so some techniques of the tensor network technology. So now we can write the MPO in the desired form. the Hamiltonian in the desired MPO form. But the cost that we have to pay is that because we have all-to-all couplings, so a non-local, if we want, Hamiltonian in momentum space, this means that we are going to have a very high, a relatively high cost of representing the Hamiltonian in this form. It's still much better than the Hamiltonian that I would have if I represent it as a matrix, but it has a relatively high cost compared to a lattice model with local interactions. Yes.
Can you put some sort of a grand canonical picture where you put some cost and play with the cost?
Yes, so this is something that we haven't tried. It's a good idea. Yeah, so an effective cost of how much we preserve the momentum. And by the way, there are lots of other ways to improve to ameliorate basically the cost of the representation that we haven't tried, and there is plenty of space for trial and error. But if we don't do any optimization, what we have is that the bond dimension, that is the size of the bonds, that the auxiliary bonds of the tensor network, increase relatively quickly with the cutoff K max which determines how many momentum modes we have in the system. So you see that it increases polynomially, while for lattice models with local interactions, it's actually, there is an upper bound. Next. Okay, but we still say, we can say, okay, I have this cost, but it's better than exact diagonalization, putting a matrix in the computer, having all these memory problems. So let's see what we get, despite the limitations that we have in the maximum maximum number of momentum modes that we can put in the system. Okay, so I'm going to show now some results for ground state and low energy excitations, and for quench dynamics, that is out of equilibrium dynamics in these models. For the Sine-Gordon model, just a few words about as motivation of why one would be interested in studying it. It's a model that has non-trivial field topology, and this means that there are soliton excitations. As in the classical system, it's integrable, so solitons interact with each other elastically, which allows us to actually get analytical predictions for this system. And has an interesting Kosterlitz-Thouless phase transition, and there is also one line of the phase diagram where M is the mass, delta is the interaction, parameterization of the interaction, where the model becomes exactly free in terms of the dual fermionic representation. So we can use these analytical results, predictions, to benchmark, to check how accurate is the method. Okay, so here is one of the plots that we got for the energy gap, the distance between the ground state and the first excited state, as a function of the parameter beta of the model. And we see that for a large range of values of beta, the description is quite good, so the crosses are numerical data and the continuous line is exact analytical results. But as we approach the free fermion point, which is, by the way, exactly the point where the model has an infinite energy, ground state energy, so the ground state energy diverges, and one has to subtract by counterterms and all that. At that point, we get much slower convergence. So when we increase the cutoff, we see significant difference from one curve to the other. When, on the other hand, we do extrapolation, when we increase the cutoff and extrapolate to K max goes to infinity, then our data points, despite the fact that they are just a few, they point to the right direction. So we get an estimate, low accuracy, low precision measurement of 2% maybe, but still close to the theoretical value, which is 2 for the energy gap. Okay, so that's not impressive. Yes?
Is this function continuous?
It's continuous. It has. This one is not continuous. Well, it's continuous, but it has not a cusp, but it has a discontinuity in the second derivative at beta is equal to square root of 4 pi, which is this free fermion point. So beyond that, it's exactly 2. So this line separates the attractive from the repulsive regime in the fermionic representation. So on the left we have attractive interaction between the solitons, so they form breathers and blah blah. On the right hand side we have repulsive interaction, so that's why the lowest excitations are 2 fermion, 1 fermion and 1 antifermion, and that's why the energy gap is exactly 2 in the units of the soliton mass. Okay, so I said not impressive, still decent, but the other thing that we can get out of this is we can calculate the entanglement entropy in momentum space, and we can verify what we expect, that the entanglement increases as we approach the free fermion point and beyond, and that's why the complexity of the problem increases. Now let's go to the other model, the massive Schwinger model, which is more interesting. It's not exactly solvable. It's not integrable, so we do not have analytical prediction for that, except for one point, the massless limit, massless Schwinger model, where the model reduces in the bosonic representation to the Klein-Gordon theory. So there we have exact results for the full spectrum, and this is actually for us the free part of the Hamiltonian. But beyond that we have non-trivial effects, like we have a phase transition when we increase the parameter lambda, which corresponds to the mass of the fermions, at the value of the theta parameter being equal to pi. So we want to see this critical point, and indeed we can, if I plot the order parameter, we see that there is a jump when we cross this line, as we expected, and there is the critical point is somewhere there, and we want to locate the position of the critical point. So again, we get results that are consistent with numerical predictions, earlier numerical predictions, but they are not impressive, honestly. So what we get is 0.333, but earlier results are an order of magnitude more accurate. So we are consistent with earlier results, but not outperforming earlier methods. But where we can really get some significant and promising achievement is in the dynamics. So here we saw results for the dynamics of some observable, the cosine field, as a function of time when I start from the ground state of the free theory and I switch on the interaction abruptly. So when I do that, I bring the system out of equilibrium, and after some non-trivial transient dynamics, I expect it to reach equilibrium, hopefully. And then if I see that, then I can compare with the thermal state corresponding to that. So if I quench above the critical point, where, as you can see, probably the potential has 2 minima, then I have non-trivial dynamics, which in the end gives rise to equilibration. If instead I am below the critical point, then I have a single minimum, and that gives me oscillations about that minimum. So if we have still the limitations of small k max, and we have to extrapolate, and we don't know how to do extrapolation for out of equilibrium dynamics so far. But once we find a way, once we understand how to do extrapolation, we will have accurate results for the equilibrium state reached after a quantum quench, and then we can compare with the thermal state and check quantum ergodicity in quantum field theory. Okay, just a last plot. The advantage of the method is that in momentum space the entanglement entropy seems to saturate. We still have to understand that, but from the numerics we don't see increase of entanglement as we see in lattice simulations, in real space discretization. And that should be linked to the fact that in the interacting theory, quasi-particles are like dressed free particles. They are like particles dressed by the interactions, but otherwise they have specified momentum, and therefore we expect that we are closer to being diagonal in the theory. Okay, and with that I will close. This is a summary. We are working on future improvements. We want to optimize the technique in order to make it more efficient, and hope that we'll soon have some a technique that can be used by everyone to do numerical experiments as we do in condensed matter.
Thank you. Questions?
In out of equilibrium physics, there's some effect that's been recently observed called quantum Pella effect, which states that the farther away you are from equilibrium, the faster you go back to it. Can these methods reproduce that if you take quenches with different tokens?
Yes, yes. So we can do all the all types of out of equilibrium protocols that one would like.
Do you see this effect then?
No, I mean, to do that, we will first need to understand how to the truncation effects, how to be sure that what we measure is has converged. Otherwise, none of these.
Well, they saturate there. So the question is how fast they saturate when you increase the cutoff.
Yes, but when I increase the cut, we have strong limitations on the cutoff K max. So when I increase the cutoff, I need to see convergence as a function of K max, not only as a function of time. And that's where we have algebraic decay of the corrections, but we are still unable to do extrapolation sufficiently well to get accurate results.
George?
Thanks for a very interesting talk, Spiros, and also for introducing, being introductory and pedagogical, in the beginning. So since you went fast on the very last talk about the comparative advantage of your method when it comes to quenches and out of equilibrium dynamics, could you repeat perhaps for which model did you study this in? Was it the massive Schwinger? Was it the Sine-Gordon?
The dynamics is for the massive Schwinger, yes. Not for the Sine-Gordon.
So non-integrable, did you say?
It's non-integrable. We expect the system to equilibrate to a thermal state, right, if everything goes well. Which is still, I mean, there are counter arguments for QFTs. We can talk about that. And I mean, if I was talking to a smaller community, I would have to present results for earlier results based on lattice discretization, which are quite few actually. I know 2 papers only doing quenches, and they were much more limited in the parameter regime. So here we quenched beyond the critical point, while earlier works have studied only quenches of this red type. So basically small deformations of the potential, where we still have one minimum. Because they very quickly, the entanglement in real space increases very quickly, linearly, and that means that after some time we cannot simulate the system dynamics. While in our case, the entanglement stops increasing and saturates at some point as a function of time, which means that, well, we can simulate, in principle, arbitrarily large times. The problem is that you don't know what you are missing out by applying the cutoff, the truncation cutoff. So we are still working in trying to find the optimal trade-off between bond dimension, which increases the cost of the simulations, and truncation. So we are trying to find a combination of truncation both of the tensor network, bond dimension, and of the K max, which which is the number of degrees of freedom in our system. So we are confident about the saturation as a function of time, but we can't yet see how fast all of these quantities converge when we increase the cutoff.
But my question is, how are you confident that your method is superior to previous methods? Do you have an estimate of the error you are making? What are you comparing with to be able to say that this is an accurate, description of?
So the difference is in the qualitative, in the scaling of the entanglement. In one case, it increases linearly with time. In the other case, it stops increasing, which means that you can reach large times, while previous other methods stop at some point and they don't see equilibration at all. That's the only thing. In numbers, it's still not. We are, in order to be able to do a comparison. Well, this is something we should do at some point. Take the same model, the same parameters, and check what we get from one method to the other.
Exactly.
Yeah, this we haven't done.
Thanks.
Okay. Other questions? Okay. One more with our guest. Thank you.
Very quick question. Thank you for the nice talk. I just thought something that in this tractation method. I mean, this reminds me of the effect of field theory, right? So after some point, we integrate the heavy degrees of freedom, which is equivalent if you sum up, let me say, the heavy energy states. Is it okay, or is it correct what I'm saying, or not?
You mean in the sense of, I'm not sure what you mean. What you mean?
If you are doing effective theory,
yes,
you treat some degrees of some field as a heavy degree of freedom, and you integrate it out, and you end up with effective theory, which is maybe equivalent with this tractation method where you are doing. This is what I'm thinking.
Yes. So in fact, this has been used by Ritschkoff in his treatment.
Actually, yes, you're right.
In his treatment of the Hamiltonian truncation, he took into account the effect of high energy degrees of freedom in exactly this way. But he used perturbation theory to treat the high energy.
So is this better, or how do you compare this method with what we are doing?
Okay, so that method is better in that it takes into account some effects that are beyond the cutoff. But it's worse in the sense that I'm still limited to whatever I can represent as a matrix in a computer. So I have the same memory limitations. Our method is better in that eventually we can do the same. We can integrate out the high energy degrees of freedom analytically to improve our estimates semi-analytically.
Okay. I have a few questions, but in the interest of time, I will defer. So, shall we move to the next speaker? While we wait for the technical presentation, so I'm very happy to introduce Professor Christos Harmosis, who started in Thessaloniki, then he did his PhD in France, in Tours, and after going to England and then the States at Florida University.
You know everything.
Now he went back to France at Paris-Saclay, right?
Yes.
Yes, in Orsay. So he's going to talk to us about black holes with primary scalar.
So thank you very much. Thank you very much for inviting me, giving me this chance to talk again here. It is very nice to come back to Athens. So this fourth talk is again in a different subject. Now it's going to be basically general relativity and a bit beyond. So we're going to talk about static and spherically symmetric black holes. Nothing fancy about it. You will see how we try to, all the things we have to do in order to go just beyond the Schwarzschild black hole in scalar tensor theories. Okay? So this is work that I've been doing since 2013. That's a long time. With Evgeny Babichev, we started working on this, the basic idea. And then more recently in 2023 with Panagiotta and Thanasis and Thodoris from Ioannina at the time, and Nico Raleker, who was my student in France. We constructed these solutions, and only later, in 2025, we started looking at the perturbation theory and talk about their stability. So, here we are. So it is clear that we're living a revolutionary time in black hole physics in terms of observations. You know that since 2015 we have binaries of black holes that we can actually detect gravitational wave signals from compact binaries. And there's many of them that you've heard about. The one in 2017, which showed us that gravity waves go at the speed of light, at least close to flat spacetime, and gave a lot of constraints in modified gravity theories for dark energy, which I will not be talking here about, but we will see it as it goes along. There were some other examples and some puzzles coming in GR, where we have a couple of binaries where the secondary, which we don't know what it is, has a mass which is 2.59 of a solar mass, which is too heavy for a neutron star in general relativity and too light for a black hole, which is supposed to be about 5 astrophysical solar masses to have the smaller black hole. So there are things which it's not that we don't understand, they're quite surprising, and a lot more surprises will come along with new observations, especially with the Einstein telescope with LISA, which will, work much further, and things like gravity plus. Well, let me go to this next one. We have the radio telescope, the Event Horizon telescope, that gave us the well-known image, and some more image of our Milky Way more recently. We have the very large telescopes situated in Chile, which is Gravity, and now it's called Gravity Plus, the updated form. You see it hasn't been updated here, where the idea is that we know that in the center of our Milky Way, very close to the center, there's Sagittarius A, which when we understand it should be a black hole, because it's like 10 to the 6 million solar masses, if I'm not mistaken. It's very big, very massive. And what gravity managed to do by combining the photons, what they see from different telescopes in very complicated ways, they anchor themselves close to Sagittarius, to a star, and then follow the star trajectories, just like we used to follow planets for the sun, to understand. And understanding the trajectories to higher post-Newtonian order, okay? Now these are still at about 1600 Schwarzschild radii, far away from the supermassive black hole. So understanding these trajectories, for example, like we did for the advance of the perihelion of Mercury, they can measure the mass of the supermassive black hole. They've already done this, and this agrees with what we understand from other astrophysical ways of observing the mass of the Sagittarius A. But with Gravity Plus in particular, and following stars like the closest one was S2, that was quite eccentric, so it had a very thickened out, flattened ellipse. Okay. There's even, they found very recently S301, which has even better eccentricity and is closer to the black hole. So the hope there is to be able to measure the rotation of the black hole and also be able to go to even higher momenta and evaluate the quadrupole and then verify if the no-hair correspondence for Kerr is true or not. You see, then you would have a direct proof that you have a Kerr black hole or not, for example. But this is very hard. It's very, very difficult. Okay? Why? But the thing is that the closer you are and the bigger eccentricity, the more relativistic and gravitational effects you have. And not only that, the fact that you can actually observe how the star goes to the apocenter many more times, so the periodicity is bigger, so you have more points. Okay. So now, you know, in maybe a few years we'll be able to measure all these things, and also the nicer, like the equation of state of neutron stars, etc. And it is understood, okay, that up to now GR sort of works very well. I mean, you know, for black holes, at least the neutron stars, and with a tiny cosmological constant, which we accept or not, and now it seems maybe not to be a cosmological constant, it works pretty well, but we know the ultraviolet, we have to correct it somehow. So the aim of what we do is to work from a bottom-up approach, so work from GR, try to go to the next level, introduce a new degree of freedom, because there is what is called the Lovelock theorem that tells us that spin 2 massless is only GR, so if we want something more, we really have to introduce a new degree of freedom. We will introduce a scalar degree of freedom. Can we find alternatives to GR black holes, and see what kind of effects we have then, okay, and how we could compare them, okay, in light of future observations. So the plan of my talk is I will just showcase what happens for Hordensky theories and beyond Hordensky theories. There's nothing special about this, it's just a mathematical framework from which to start with, from bottom up, as a measurable departure from GR with one extra degree of freedom. We will construct black holes with primary hair. One of the questions that is open is, can we have solutions which are everywhere regular, which are covered by a horizon, which we will discuss a little bit. And then, if I have time, I will discuss axial perturbations, and then we will meet the difference, a notable difference from the GR, with the notion of effective and different background metric. I will explain what this means. I will explain to you the key notions we will see here, primary and secondary hair. I hope, leaving this room, you will know what exactly they are. These formal transformations, this is just some kind of construction, like a conformal transformation of a metric. You will see what that is. It will be very important, as always in physics, to have some local or global symmetry in order to be able to find explicit solutions. And again, I will say a few words about effective and background metrics. These are the things we will encounter during this talk. Okay. So, scalar tensor theories go back to Brans-Dicke, etc., etc. Okay, but they were developed in the 74 by Hordensky, and as it was discovered again by generalized Galilean, by these people that you see there. And then they was constructed beyond Hordensky and those theories. All these theories have a common denominator. They have a spin 2 graviton, which is massless, and one only extra scalar, okay, and no ghosts, okay. So these are very generic theories. They are, let me just show you for Hordensky, for example, you have all these operators that give you still second order field equations. That's what Hordensky showed in his working with Lovelock, which had done the same work for spin 2 in higher dimensions. So, but they're very general theories, because you see you have G2, G4, and G5, these four functions of phi and the kinetic term, x, which are free functions instead of having just one Planck constant. And within it, of course, lies G4 equal to 1, the case of general relativity. Now, there's nothing fundamental about the scalar tensor theories. I mean, they don't have, it's just, we know the general framework, where we have, if you like, up to second order equations of motion, or if we have higher order equations of motion, that they're still not ghosts, they are degenerate theories. But what the interesting thing about scalar tensor theories is that they are limits of more complex and fundamental theories. There's nothing fundamental about them, okay? Like massive gravity, like brain world models we met ages ago, or effective field theories coming from string theory. We know that there is at least one scalar mode there, maybe even infinite number of them. Lovelock theories in higher dimensions, etc. The point is that all these theories, they have a limit, just like GR has a limit which is Newtonian. These theories have a limit where they are GR-like plus an extra scalar degree of freedom. Yes?
Since you mentioned the EFT from theory, these theories are not always, let's say, out of the swamp line. They might be like, do they always have as EFTs well-defined degree completion? Or,
No, not necessarily. I'm just saying that
they could. Some of them could. Not
yes,
all.
yes, yes,
Okay.
yes. So there are limits of more fundamental theories, okay? And it's like a bottom-up approach where I know GR, I don't do nothing fancy, I'm just adding a degree of freedom, and I have this enormous class of theories I can go to and see what I can find, okay? So, as I showed you before, Hordensky is parameterized by 4 functions of the scalar and the kinetic term x that you will meet throughout this talk. I mean, you will see this coming up a lot. And it's quite interesting that my French friends that you see up there, mostly French, okay, and collaborators for some of them, they discovered also beyond Hordensky or DOS theories, which in principle can have higher derivatives, but at the end of the day, they end up being conformal and disformal transformations of Hordensky theory. So Hordensky theory, I don't have my glasses so I don't see very well. So Hordensky theory, if I do a conformal and disformal transformation depending on phi only, is an internal map. They take me again into Hordensky, a different theory but still Hordensky. But if I do now a disformal of depending on x of Hordensky theory, then I go to beyond Hordensky theory, which has one more degree of freedom, which is exactly this disformal transformation. And if I do a conformal of beyond Hordensky, I go to DOS type 1, which is the one which is acceptable for other phenomenological reasons. So basically, these DOS theories, which are the most general, let's say, healthy theories in scalar tensor, they're described not only by the 4 Hordensky functions, but also by one more, which corresponds to conformal, and another one which corresponds to disformal transformations. Okay? Now, I don't want to go further about this, but this is the background of theories we have. Vast background. Okay? So, now we want to look for theories which have solutions. So, in general, when we're looking for solutions, we shine the light where there is more symmetry. Okay? That's what we do. Not necessarily what nature does, but this is what we do. So, in 2013, therefore, we considered the case where we had only G2 and G4 of Hordensky, and we just took a linear theory in couplings, where G2 has the cosmological constant and the canonical kinetic term, and G4 has got this Einstein-Hilbert term, of course, because this is the constant term, as I told you, and it has this fancy Einstein term coupling to the scalar, which is beyond GR, of course. Okay, this is the modified gravity term. Now, the theory is interesting for us because it has a global shift for the scalar, so you can shift the scalar by a constant because, as you see here, everything depends on in the action on the derivatives of the scalar, not the scalar itself. So there's no potential term, for example. And it has parity symmetry. It means that you have up to even number of derivatives of the scalar field. Nothing, so there's no G3 and G5 here, if you like. Because of the global shift symmetry, you have that the scalar field equation can be written as a conserved current equation here. Okay, and this is very important. So the scalar field equation has this form. And surprisingly, you can find the general static and spherically symmetric solution of this theory. And amongst the solutions that you find is this de Sitter-Schwarzschild black hole, a stealth solution, stealth Y, stealth because there is a non-trivial scalar that you see here, but the metric is exactly like a GR metric. So this is a bit boring, okay? So we're not finding something new. We're finding these de Sitter-Schwarzschild black holes. We were interested at the time because they are sort of self-tuning solutions, okay, because they have an effective cosmological constant which is different from the background cosmological constant that is given by lambda. So this could be interesting for dark energy, whatever. Many of these solutions are ruled out, in particular this one, because of the gravity wave signals. But nevertheless, I show it to you here because it's an example where you have a solution where Q is an integration constant, which is not primary here, it is secondary here, because it can affect the metric, but it is always coupled to the coupling constants of the theory. It's not free, okay? Now, the second thing which is a bit crazy about these solutions is that you can see that the scalar field, now the metric has a killing vector, a time-like vector, it's static, I told you, but the scalar field isn't. It is linear in time. And the fact you can have it to be linear in time is precisely because of the symmetry, because your theory only depends on derivatives of the scalar. So when I write down the equations of motion, okay, I won't have PDEs, I will still have ODEs depending on R, because any derivatives of time will be gone away, but nevertheless, Q will appear as a parameter of the system, or to be more precise, an integration constant of the system. And this is the idea now of constructing, going beyond the O'Hare theorem. In which sense? Shift symmetry allows me for linear time dependence. So the idea, okay, this goes back to actually works by Horowitz and I think Oscar Diaz in string theory, where they use this idea that the associated energy momentum tensor here in red, associated to the scalar, okay, has the same symmetries as the metric. D by dt is a killing vector, but not the scalar itself. By breaking this for the scalar field in a mathematical robust way, you manage to have a kind of scalar hair for your solution, which is not modifying GR exactly yet, except for the cosmological constant here, but this is important for what will follow. The second important thing that for what follows is that what I noted in the second bullet point here. You see, it seems like this guy here, and this is another problem that happens with heavy solutions in general. When you approach the horizon, the scalar field tends to explode, as it does. You see, it does it here also. But because of the time dependence, okay, you must remember that in Schwarzschild gauge, which is an observer far away, he never sees something cross the horizon because the time goes to infinity at the same time. So in fact, this looks singular, but when you take into account the fact that f goes to 0 while t goes to infinity, you can go to advanced Eddington-Finkelstein coordinates, and you actually see that the scalar is regular at the horizon for all q. Okay? Now, a second way that people have to consider secondary black hole hair is that, for example, in Gauss-Bonnet black holes, is that in order for you to be, your scalar to be well defined at the horizon, you fix the scalar charge so to make the horizon regular, the scalar at the horizon regular. Here, what is quite important is that phi is regular for all q. Our problem is that q does not appear as an independent integration constant in the metric itself. And so this is what we will seek to do now. Okay? This is the idea. And the second point that was used by my Japanese colleagues here, Kobayashi and Tanahashi, after our paper, was to note that this solution actually had X constant, and actually then you can generalize these stealth solutions in those theories very easily. Okay? Now, so let us go now and consider a theory which is again shift symmetry, G2, G4, and F4. Okay? And this is what is called beyond Hodensky. So I'm taking this general theory now rather than this previous one. And I'm taking static and spherically symmetric solutions with the same ansatz for the scalar. It has this time dependence, which is allowed. I cannot have anything else, right? This is it. And then, you see, the equations of motion are completely chaotic. But after staring at them several times for several cases, you see that when you make this simple theory parameterization, where the beyond Hordensky term couples with all these guys, and you call this Z, you end up with an intercoupled system in the sense that I will show, what I will explain now. Then the field equations simply boil down to this thing there. Okay? So you see the first term, for example, tells you that you can integrate that. Tells you something very simple, that if you want a homogeneous solution, F equal to H in your black hole, like Schwarzschild black hole, you cannot have it for any theory, but you can only have it for theories such that Z is a constant. Then you can have it. Actually, it's if and only if. Okay? So, for example, if I have Z to be a constant, then my second theory, my second equation, my second equation here is absent of any derivatives of the metric. If I tell you what theory you have, this equation algebraically gives me X, therefore the scalar field for my solution. And once I know what the scalar field is, I input it in here, and I can just integrate to find the metric. And that's it. So so at the end it seemed very complicated, but it's actually very easy. Let us look at what happens for homogeneous solutions. So I take Z to be a constant. And as I said, I have to give you the theory, okay? So the theory, let me just take these analytic prototypes. I take P to be positive, actually half integer, positive half integer. So something regular, okay? Eta and lambda are coupling constants, and P is just the power. And if I put that in there, I get this simple equation, a scalar equation, which immediately gives me X here and the scalar field here, okay? And this is true for any P, for any of these theories up there. X is the kinetic term, okay? And then when we solve for the metric, we find the first part is Schwarzschild because we have GR, plus another part now, which depends on Xi, which is an independent integration constant originating from Q, I was telling you here. So Q now appears in the metric and appears as a second charge, which is completely free because the solution is actually regular for the scalar. And indeed, as I told you, the scalar field can be written in this way, and you can go and calculate the nether charge, and the JT part of this gives me precisely the nether charge associated to my primary hair, which is over there. So this is a black hole with primary hair that obviously modifies the general relativity solution. And you see when Q is 0, this is trivial, phi is trivial, and I get back to GR. Okay? So this is what we found. And let us now just look at some examples. In fact, what is important is that the scalar charge I told you is finite for P greater than 3/2, and this will be important for the regularity of the solution. So when it's C2, the theories are C2 in this case, at least. So for P equal to 1/2, which is not in this case here, we have a solution which is a stealth solution again. We have a GR solution with X non-constant. And funnily enough, this is the only solution which is homogeneous and is in Hordensky theory. If I take P equal to 1, I have a canonical kinetic term, and I have this solution here. Again, we're not in the case P greater than 3/2, and then the solution is only locally asymptotically flat, because you see, you don't go to 1 far away. By the way, you can put here a cosmological constant, it's not a problem, but I'm only looking at asymptotically flat cases here. So I don't go to 1 far away, I go to this factor, and in fact, what I have in this case is a solid deficit angle, okay? So the solution is only locally asymptotically flat. Topologically, you don't have a sphere, but you take out a wedge, like when you do from a watermelon, you take out a piece like this. And the far-away effects of this are very similar to a gravitational monopole first described by Bariola and Vilenkin. So this would be the effect of the p equal to 1 black hole. For p equal to 2, now we are in the regular region, okay, and then we have these type of solutions. I will go back in a few moments. And 5 halves, etc., we have solutions that we can find. So the second question is, what is the asymptotic structure and what are the possible horizons we have? All right. So far away, the black hole behaves much like Reise-Nordstrom. So Xi is a bit like an electric charge, which can be either imaginary or not. While close to the origin, well, we have this part here, which is like a Coulomb singularity. Remember, we have a singularity at the center anyway. But we have a regular term appearing here. And basically, as I showed you here, this is what was more or less Xi before. This is Xi, in fact. And when you see, when my coupling constant is negative, so my Xi is negative, this is Schwarzschild, and basically I have a black hole which is fatter for the same mass. Okay? This is what's happening. But when Xi is positive, things start getting more interesting. So this is Schwarzschild again. Okay? Now I raise Xi, and all of a sudden I can have 3 horizons. I raise Xi some more, then I can have something which is like Reise-Nordstrom, because in the inner horizon and outer event horizon. And then at some point, if Xi is too big, then I have a naked singularity, like we have horizon. So these are the basic things for p equal to 2, but also would be the case for the other p's, for greater than 3 halves. Now, the interesting thing is that, you see, there is a point, as I showed you here, close to R. There is a point where these things can actually cancel each other out, and then surprisingly, without any fine-tuning at all in the coupling constants of the theory, I end up having a regular solution, a solution which at the center has no curvature singularity. It's actually C infinity. Okay? And depending on how big the mass is, because Xi and mu are now fixed, depending how heavy my object is, I can have a soliton, or I can have a black hole, a regular black hole. So this is at the end point. This is the biggest Xi can be. Okay? So this is a bit strange and I think quite unstable, because here we don't have, having a regular black hole is kind of promising for proper ultraviolet theories, in the sense that ultraviolet complete theories. But the point here is, I think, that if I have this object, and imagine that I'm sitting at this mass and Xi particular point where this thing is completely regular, and I put a speck of dust inside, most probably it will become a naked singularity. Or if I reduce Xi, it is very difficult for this to be a stable solution and the result of matter inform, which of course we haven't done here. But it is something promising in the sense that ultraviolet completion may solve the central curvature singularity, and here it seems that in this theory, this extra scalar charge can do this, even in this way. And I'm putting away problems about the Cauchy horizon, etc., etc. Okay? But this is an effect that we find for these solutions without looking for it. It's just there, and it's a general effect. Okay. Now, what about the non-homogeneous solutions? Well, a simple mathematical analysis shows you that any non-homogeneous solution I can construct from homogeneous ones by, remember what I call this formal transformation. Okay? So this formal transformation you can show take us from homogeneous to non-homogeneous black holes. So you have, it's really an integrable system. So basically, Z, the part of the theory that was fixing how the solution was homogeneous or non-homogeneous, and D of X are mathematically equivalent, and they define a class of equivalence, okay, which is defined modulo Z, taking us from any homogeneous to non-homogeneous solution. So I just chose 2 frames. When you do this formal transformation, what is interesting is that you change the speed of graviton waves, okay? And there is one frame which is precisely the frame where the gravitons go at the speed of light. This is this frame here, which is defined by this Z and this D. So they're equivalent, okay? Another frame which is interesting is the frame where we're in pure Hordensky. So F4 is 0, and this is defined by this D and by this Z, basically. Okay? So this is the, let me go to P equal to 2 to give you the examples. This was the homogeneous solution where Z was constant. And this is the solution which is now non-homogeneous, okay, and corresponds to this frame. They belong in the same equivalence class, modulo Z. And this is the solution which is the Hordensky one. Again, non-homogeneous, but belonging only in Hordensky. My point is that all of these solutions you can have by a simple disformal transformation. And it so happens that when P is greater than 3/2, we have a finite nether charge. These solutions have the same characteristics, the same regular black hole, the same horizons, the same regularity property, something which is not true when you don't have a finite nether charge. So the finiteness of the nether charge seems to help with the properties also of the black hole. Okay, so this is in summary what we have. We have two independent charges, the mass and the scalar charge. Okay, and we have, I didn't showcase it here, one more coupling constant which basically tells us how big the effect of the scalar is beyond the horizon, inside the horizon, further even out, etc., etc. Okay, so this is the nether charge, as we saw there. And we have good asymptotics, horizons for all solutions in the same disformal class. We have a regular black hole at the end point of the biggest psi possible, okay? And we have a regular scalar for all Q at all future horizons. So the solution is really regular, apart from course at R equal to 0. Then you can also mathematically add sources, etc., and have more complicated functions, but let's not go into that. Now, let me now move on to black hole perturbations. How much time do I have?
12 minutes.
Okay, I should finish before. So, gravitational wave astronomy provides us a window to test gravity, and in particular when you have binaries. Of course, we start from ppn, then we go to numerical, and when the binaries collide together and they form, say, a black hole, basically they will just ring down. The ring down phase would just a few perturbations and just go back to a static black hole or a stationary black hole. So at this phase, the ring down phase, we can understand things about knowing black hole perturbation theory and quasi-normal modes, for example. We can understand and compare them to gravitational wave binaries at the ring down phase. Okay, with black hole perturbation theory. So perturbation theory is very important. And basically, we do exactly as we do in GR. We go to the frequency domain, expand in spherical harmonics. We have axial and polar modes, and we choose our Sturm-Liouville problem, and we solve it in the Schrödinger form, where it's basically flat. Okay, we go to these coordinates. Then it's a Wheeler gauge, as we call it in GR. And it so happens in GR that the effective metric, where gravities are going to propagate, and the background metric are identical. That's normal because you only have one metric. Here we have new degrees of freedom. So in scalar tensor theories, we have the monopole, we have the breather mode, so one extra scalar mode. Okay, you don't have a Kirchhoff theorem here. And secondly, we have again one axial mode, but as we will see, the effective and background metrics are now different. And I will explain what this means. Basically, it will be just like we have in Horava gravity, where we have a spontaneous Lorentz symmetry breaking, and photons and gravitons can see different sizes of spacetime. So we go. This is exactly what we do in GR. We end up with a Schrödinger equation with an effective potential. This is our tortoise coordinate. This is classical here, okay? And we have this effective potential for axial perturbation. given here. And the characteristic is that it depends on the modes L, etc., the mass of the black hole. FGR here, this is F of square. This is what we have in GR. So what is the image of this for these theories, putting aside technicalities, which are quite complicated? You end up with the same type of potential, you see, except that there is a part depending on the theory, okay, which can be quite complicated, but it doesn't matter here. And phi is not my background metric, you see, it is the same form, huh? Except that phi is not my background metric f, which was already changed compared to GR, but it's shifted by this pattern. So the background metric and the effective metric are different by this shift. And this is because the scalar modes, although we're looking at the axial modes, perturbation order, it starts to interfere with the axial mode of spin 2. Okay? And it so happens, you can show for the theories that we have here, that the effective metric, where the axial gravitons propagate, is not the background metric. It is exactly the frame where the graviton speed is the speed of light with a conformal factor equal to 1. It's like an Einstein frame in higher order gravity. Okay? This is what it is. So that means that gravitons see a different metric other than light, okay, or matter close to the black hole horizon. The axial perturbations are stable. You can show this by inputting the usual boundary conditions, outgoing and ingoing into the horizon. They are dissipative. You can have quasi-normal modes, etc. But the potential is positive definite. And as long as the effective metric I was showing you before is well defined, which is true for a scalar up to this point here, for each p, your perturbations are going to be stable. So let me show you here, I think on the left, this is my background metric, this is my solution basically, how the horizons go, okay, for different values of psi. And on the same column, for each column you have the same psi, if you like, here and here, but this is the effective metric, what axial gravitons is. And this is the phase space of the solution, here, here. And this is the zoom in of this. And the point is that as psi is negative, I have a more fat black hole, nothing happens here. If I increase psi, however, then we come to a point which is a line which is a regular black hole, which is always there, and it's the same for the effective and background metric, thankfully. Okay? And then it can be that for the background metric I have an anti-singularity, whereas for the other one I'm still within the horizon. Okay? So these are the effects that you have because of the scalar. So let me conclude. So we have constructed these primary Hare black holes. You can put electric charge to them, cosmological constant and all that. We saw that the solution becomes regular at the origin. Okay, this is one characteristic of the solution. So you have regular black holes. You can have the homogeneous and non-homogeneous black holes. If you're not interested beyond Kordensky, you can go to non-homogeneous Kordensky black holes, and they are described by this theory function Z equal to Z. Axial gravitons are regular and well behaved for this solution. So we have axial stability for most psi. Now for polar perturbations, things are far more difficult. We are sort of looking at the monopole problem for this now. It so happens that there is no notion of effective metric in this case. It's very complicated, but some of the examples that we see here show us that in certain cases we have stability or also instability. Okay? And the open question still remains how we could find rotating counterparts of these solutions. We're also working on neutron stars coming from such theories and see how they change what happens to the general relativistic frame case from neutron stars. Thank you for your attention.
some of the famous experiments of GR, like bending of light or the perception of the continuum in these generalized theories, do you find some bounds?
Yes. So you can do this, for example, for the S2 star, already at very strong gravity. You would find, I mean, these solutions generically shift the ADM mass. Psi shifts the ADM mass. That's why you can have also a regular solution, right? Because they compete between each other. But what you call the ADM mass is what you see at infinity. So for example here, if you had a way of measuring the mass coming from astrophysics, from electromagnetic waves, and if you had and measured the mass from trajectories, you would see a difference, then you would be able to say that psi cannot be bigger or smaller than this and that. But it's still very early, we don't have good enough bounds for this.
So generically they enhance the phenomena or they make them smaller?
It depends. If psi is smaller, if psi is less than 0, okay, then in fact the horizon is fatter. And then the best constraint comes from nucleons, because nucleons, though they don't have a horizon, they're very small in size, they have a specific mass, and you see that there, psi has to be actually minute, very, very small, not to create a horizon. So you're not allowed. If psi is positive, you have more compact objects, extremely more compact objects, and then the kind of constraint you could have, apart from the one I told you, is that since I observe a mass which is so many solar masses, and for certain psi, beyond certain psi I will have a naked singularity, these psi's are ruled out, for example. But these are early on. You can find all of these things.
Yeah, thank you for the very nice talk. Okay, so given that you mentioned also gravitational waves, is this something that you think could be observed with the methods we have today, or maybe even with future detectors? And even more so, I mean, yeah, the theory is there. Do you think, or do you have plans to maybe numerically solve very black holes, binary stars?
People have started looking at this, especially for the theory of Gauss-Bonnet black holes, because this has been going on for a longer time, if you like, not for any particular other reason. Yeah, in principle, in future, observations will give us things which I'm sure we won't expect. Now, where I expect more interesting things to happen is for smaller black holes, not these supermassive black holes, because supermassive black holes, the problem is that their horizon is extremely flat. So curvature is very small, in fact. It seems counterintuitive. Whereas small black holes, not that small, but smaller black holes, that we would find in binaries, may constrain things, are closer to the ultraviolet, and we might find some effects there. But for the moment, all the numerical stuff, I think, which we use in gravitational waves is coming from GR. So it's important. But the problem is which of the theories? You see, this is vast.
Exactly, but do you think also it's possible, because I guess it's more complicated than doing just a GR calculation?
I think it's possible, but it will need a lot of work. Yeah. We're not there yet. We don't understand the perturbation field.
And I guess for neutron stars it's not even worse, probably.
Neutron stars, exactly, it's even worse.
So.
But there the effects are more important because you can have equations of state which are completely different from GR.
Right.
You can have very compact equations, which are not allowed in GR.
Thank you.
Thanks, Christos, for the very nice talk. I could comment, a cryptic comment you made in the beginning about the state of the art of the cosmological quantum.
Ah, yes, okay.
So do you want to say more of it?
No, but there's been baryon-acoustic oscillators have been oscillations.
This discrepancy.
Yeah, there is some kind of cosmological discrepancy. I'm not.
The redshift, you mean?
Yeah. So it may be the cosmological constant, not that constant after all. But I was thinking of the small cosmological constant being maybe an effect of something else, dark energy being, some modified gravity.
The data still support the W equals to -1. Okay.
That's what I meant.
Yeah, okay, thank you.
Very interesting talk, Christoph. Just to maybe clarify a little bit, add on the previous question. So this class of models you presented, they are of course constrained by existing astrophysical observations. For example, the fact that gravitational waves travel with the speed of light, that already carves out some of the fact.
No, let me cut you off here. So in the first solution I showed, you had a dark energy solution. Now the scalar here, what it does, it is not a dark energy scalar. It doesn't modify. Dark energy is again a small cosmological constant. The modification I have here is an ultraviolet modification. So what I mean by that, GR is an effective theory. So it might be the ultraviolet. There is some modification of this type. That's what I'm saying. At the infrared, I'm not considering any modification. This G4 term would have been ruled out. But if you take these solutions where phi is not a dark energy field, so it's not changing what happens far away from the black hole. It's not a cosmological effect. If we actually calculated the time it took if we had an event close to the event horizon, okay, of the black hole, and we counted, because axial gravitons you saw move in a different metric than light, okay? And if you count the effect, in this case it's 10 to the minus 6 seconds, whereas in the gravitational wave 17, it was like 7 seconds. So we're well within the bounds. And the reason is that the scalar is only modifying things close to the horizon, not far away. So this is not a dark energy solution. It's not a cosmological solution. So my point is that it might be that indeed for dark energy, these kind of theories are indeed ruled out. But I'm looking at ultraviolet corrections and not dark energy corrections.
If it's ultraviolet, how can we actually measure falsify them or not in the future?
By looking at black holes, by looking at observations of black holes, Einstein telescope, Event Horizon telescope, and small black holes.
Okay, Nico, last question so that we can all go for lunch.
The theory that you consider, to have this higher order scattering and so on, but they're not all the higher order scattering.
No.
Length, right? So these kind of solutions, are they stable?
That's what I'm looking at. For the moment, yes.
If you perturb, from those solutions, it is an effective theory, right?
Yes, in a way.
The term you left out, if you put them in, will they survive or?
If I put them in where?
Then you question for motion. This kind of solution, will it be just slightly perturbed or will it circle completely?
We are looking at small perturbations as we do for GR, and for the moment we have found stability for most cases, except if Xi gets the scalar the scalar charge is very big, then you have instability. Now we haven't looked at the polar perturbations because we haven't cleaned this up. It's not like in GR where you have one Schrödinger equation. Here you have 2 degrees of freedom which are mixed, and it's very hard to find what happens there. So the point I'm looking for these theories rather than theories which have higher derivatives. I have no problem with higher derivative theories, okay? But here I have up to second derivatives, and I can look at the problem in a specific GR type of fashion. So how could you do perturbation theory with fourth order derivatives? Here I can introduce boundary conditions which are usual in a Sturm-Liouville problem and see what happens. In this sense, it's bottom up. But I'm not saying this is some ultraviolet completion of GR.
Okay. In the interest of time, let's stop now. Thank you very much again. We're going to break for lunch. I suggest we do 1 hour. So we start at 2:45. 2:45. Better to have more time for lunch than for coffee afterwards. If you know your way around, there are very many places where you can have lunch. There's the Korai area.
Still open.
Yeah, well,
It is open.
It is.